Saturn stands out among all known planets for having the most precisely aligned magnetic field with its rotation axis. The discrepancy between these axes is astonishingly small, less than 0.06 degrees, a rarity in the solar system. This finding comes from extensive data gathered by the Cassini spacecraft, which orbited Saturn from 2004 to 2017. Scientists initially expected to observe some level of misalignment, similar to the magnetic fields of Jupiter or Earth, but Cassini's observations challenged all theoretical predictions. Planetary magnetic fields are produced through a process known as the dynamo effect, which relies on the movement of conductive, rotating fluids within a planet. For this system to operate, an unevenness or asymmetry is typically required to sustain the dynamo. When a field becomes nearly symmetrical, as with Saturn, existing models suggest the dynamo would falter. Saturn, however, remains magnetically active, leading to speculation about processes that aren't fully understood. One leading hypothesis is the presence of a liquid metallic helium layer encasing Saturn's core. This shell may dampen irregularities and allow only a near-perfectly aligned magnetic field to reach the planet's surface, potentially hiding a more complex tilted field deeper inside. Such a scenario would mean Saturn's internal makeup is far more intricate than previously believed. Cassini made these exceptional measurements possible, especially during its final 22 orbits, when it swooped between the rings and Saturn's atmosphere. These close passes reduced outside noise, allowing the spacecraft to track the magnetic field close to the visible cloud tops. The resulting data confirmed the field's extreme symmetry and prompted new debates about how giant planet dynamos function. Unlike Jupiter, Saturn's magnetic field lacks the asymmetry needed for rotation to be timed by radio emissions. Scientists ultimately determined the length of a day on Saturn, about 10 hours, 33 minutes, and 38 seconds, through a groundbreaking method called ring seismology. Saturn's internal vibrations produce subtle patterns in the rings, much like seismic waves on Earth, providing a unique glimpse into the planet's deep interior and enabling an accurate measurement of its rotation. A remarkable aspect of Saturn's magnetism is the absence of pole drift. Where most planets, including Earth, show magnetic poles wandering over time, Saturn's poles appear locked in place. Whether this is a long-lasting trait or something temporary remains an open question. Saturn's extensive magnetic field, which stretches millions of kilometers into space, forms a protective magnetosphere. Though weaker than Jupiter's, it shapes the environment around Saturn and interacts closely with its rings and moons. The moon Enceladus plays a dramatic part in this system. Powerful plumes of water and ice erupt from Enceladus, injecting particles into Saturn's magnetosphere. These particles ionize and help drive electrical currents, subtly shifting the planet's magnetic environment. Cassini's instruments trace these influences, revealing a dynamic interchange that is rare among planetary systems. Saturn's auroras, seen at the poles in ultraviolet and infrared, are energized not just by solar wind but also by moon-driven interactions. Charged particles ride magnetic field lines, colliding with Saturn's atmosphere and creating stunning light shows. The internal region responsible for generating Saturn's field is thought to contain metallic hydrogen, an exotic state that sustains powerful dynamos, although details of its behavior in Saturn's unique conditions remain elusive. Current computer models still struggle to recreate Saturn's remarkably aligned field, pointing to gaps in our understanding of gas giant interiors. Research suggests Saturn's core isn't a single solid chunk but a diffuse mixture of heavy elements blended with hydrogen and helium, different from what was previously imagined. This gradual transition affects both the field's generation and how it is observed from outside. The magnetic field also influences the rings, guiding particles and creating features like spokes, dark, temporary patches that Cassini documented, which seem to correlate with magnetic variations. Scientists hope the magnetic field will eventually serve as a tool to probe Saturn's interior. Over time, shifts in the field could reveal changes in internal structure and convective activity, offering a window into the evolution of the planet. Future missions may deploy atmospheric probes deep into Saturn to measure physical properties, firsthand refining our models of how planetary dynamos operate. Unlocking Saturn's secrets is vital beyond our own solar system, as many giant exoplanets may possess similar enigmatic characteristics. The ongoing effort to reproduce Saturn's magnetic landscape in simulations underscores just how much there is left to discover. The struggle to pinpoint Saturn's rotation period highlights both the ingenuity and challenge in planetary science. Since variations in the magnetic field did not provide the needed clues, as they do on Jupiter, scientists relied on the planet's own vibrations as transmitted to its rings, a celestial seismograph. These oscillations generated patterns in the rings that, when carefully analyzed, revealed the length of a Saturnian day. This innovative approach not only resolved a long-standing mystery, but also illuminated the deep fluid dynamics of the planet's interior, continuing to expand our understanding of giant worlds. Ring seismology emerged as a revolutionary technique for exploring Saturn's interior, and Cassini was the first mission to fully harness its power. Saturn's internal vibrations caused by oscillations, compressions, shears, and gravity waves create subtle but regular gravitational patterns in the planet's rings, primarily the C ring. These patterns, detected as ripples, bands, and density variations by Cassini's high-resolution instruments, act like fingerprints for specific oscillation modes within Saturn. By mapping these structures, scientists inferred the planet's true rotation period as 10 hours, 33 minutes, and 38 seconds, a figure published in 2019 after comparison with sophisticated models. This approach, more precise than earlier methods, relying on magnetic field variations or atmospheric tracking, provided direct insights into the deep hidden layers of Saturn and revealed a gradual or diffuse core region extending up to 60% of the planet's radius, challenging the notion of a solid, sharply defined core. The fine details seen in the rings, a testament to Cassini's measurement sensitivity, yielded new information about Saturn's inner density, mass distribution, and even the depth where atmospheric winds give way to a more uniform planetary rotation. The technique has proven especially valuable because it is unaffected by external factors like winds or magnetic field fluctuations and can detect deep phenomena, turning Saturn's rings into the most sensitive natural seismograph ever observed for a giant planet. Saturn's rings also opened a window on the planet's current geology and events occurring thousands of kilometers below the clouds. Scientists found that internal oscillations powered by convection, rotation, and density gradients reinforce themselves through gravitational resonance, leaving precise imprints in the rings, particularly in the C ring, which is less disturbed by moon-induced effects. Accurate separation of these planetary signatures from lunar influences was vital to lock in the results. Among Saturn's rings, the E ring is distinctive because it's constantly replenished by the tiny dynamic moon Enceladus. Unlike the ancient fragments making up the main rings, the E ring is a living structure, continually fed by geysers that launch water vapor and ice particles from Enceladus' south pole. This ongoing process keeps the ring bright, diffuse, and ever-changing, with most particles measuring just micrometers to millimeters across. Cassini observed dramatic changes in the E-ring's density and brightness, directly tied to periods of heightened geyser activity, detecting fresh particles where Enceladus orbits within the ring. Occasional flybys by Cassini allowed instruments to capture samples from these plumes, confirming they contained mostly water ice mixed with traces of organic compounds and launched at speeds up to 400 meters per second. The source of these geysers are long fractures near Enceladus's south pole, known as tiger stripes. These warm regions, measured by Cassini's thermal sensors, hint at the extraordinary presence of an internal ocean beneath the icy shell, heated by tidal forces from Saturn's gravity. Some plume material escapes to space, but much of it snows back onto Enceladus's surface, maintaining the moon's high reflectivity and blanketing it in fresh ice, making Enceladus one of the brightest objects in the solar system. This process ensures the E-ring remains vibrant and continuously refreshed, with Enceladus's activity tightly bound to the ring's evolution. Together, Cassini's use of ring seismology and its in-depth exploration of Enceladus have transformed our understanding of Saturn, revealing not only the planet's hidden rotation and layered core, but also the dynamic interplay between moons, rings, and planetary processes, setting a model for how we might one day study exoplanets with similar rings far beyond our solar system. Beneath Enceladus's frozen exterior, relentless gravitational forces from Saturn and nearby moons stretch and squeeze the moon, creating ongoing internal friction. This constant flexing generates enough heat to keep a hidden ocean of liquid water deep below the surface, even as Enceladus endures surface temperatures colder than -180 degrees Celsius. The continuous cycle of buildup and release of pressure inside the ice crust drives the geysers, making Enceladus a living, changing world. Cassini's detailed long-term observations revealed that the intensity of these eruptions varies depending on where Enceladus is in its orbit. Plumes become more powerful when the moon experiences the greatest gravitational stress. By tracking these fluctuations, scientists learned more about the structure of the crust and the likely existence of a global ocean in direct contact with rock far below. The makeup of Saturn's E-ring gives us rare insights into the chemistry of Enceladus's underground ocean, because the ring is continually refreshed with ice grains launched from active fissures on Enceladus. These particles hold clues about what lies beneath the moon's icy shell. Analysis shows the E-ring is made up almost entirely of uncontaminated ice, with barely any minerals or dust to darken it, setting it apart from older, more polluted rings elsewhere around Saturn. Yet the E-ring is temporary in cosmic terms. Each grain may last anywhere from a few centuries to several thousand years before it gets blasted away or collides with other particles. Without the constant geysers topping it up, the E-ring would quickly fade, so its continued presence is proof positive of current, ongoing geological activity on Enceladus. Enceladus is more than just a frozen moon shooting jets into space. The material it sends out directly influences Saturn's huge magnetic bubble. Charged particles from the plumes stream out, interacting with Saturn's magnetosphere and causing subtle shifts in its shape and intensity, an effect Cassini recorded using sensitive plasma detectors and magnetometers. Enceladus has become a powerful regional player, affecting not only its immediate surroundings but the entire Saturnian system. Scientists believe that the underwater ocean inside Enceladus touches a rocky floor, allowing chemical reactions between water and minerals to take place. As the fissures in the ice open, they funnel out both pressure and material altered by these reactions, sending processed substances out into space. This one-of-a-kind connection between a moon's inner ocean and the vacuum of space is incredibly rare, and makes Enceladus a top target in humankind's search for life beyond Earth. The almost pure composition of the E-ring is so reliable that researchers use it to calibrate their instruments, comparing readings against the ring's clean background to adjust for sunlight or other interference. Enceladus's steady production of fresh ice and vapor also impacts its own motion. Every burst of material ejected into space shifts the moon's mass and angular momentum just a little, affecting its orbit over time. A phenomenon scientists are still working to fully understand. These subtle changes could help explain the fine balance of Enceladus's interactions with Saturn's other moons. But Enceladus isn't just special for Saturn. Compared to other frozen moons like Triton or Europa, its plumes are far more accessible and well-studied. Future space missions are being planned right now to fly through these plumes and grab samples on the go, or perhaps even land directly in a geyser zone to explore the chemistry and potential biology up close. What Cassini found in those ejected particles was astonishing. Inside the watery spray were not just simple ice grains, but a blend of complex molecules. Scientists found organics, various salts, silica, and even hydrogen gas ingredients that are hallmarks of the most energetic, life-friendly environments on our planet. Many of these compounds, including molecular hydrogen and amorphous silica, form in places with lots of chemical energy, underwater hydrothermal vents, like those lining Earth's own ocean floors. The presence of hydrogen suggests that water deep below is reacting with iron-rich rock, a process known as serpentinization that not only powers chemical changes, but could provide fuel for living things. On Earth, some unique microorganisms feed on that exact reaction. Cassini's instruments also detected complex carbon molecules containing nitrogen and oxygen, basic ingredients for amino acids and other prebiotic chemistry. While no evidence of life was found, Enceladus has all the building blocks needed for it to begin. Scientists also found sodium and potassium, cluing us into a salty underground ocean touching mineral rock. This rich chemical diversity makes Enceladus's ocean look increasingly similar to environments on Earth, where life thrives without sunlight, powered only by chemical energy. Switching to another moon, the Cassini mission carried a small lander called Huygens, a European probe that made history by becoming the first craft to touch down in the outer solar system, landing on Titan in January 2005. During its dramatic descent, Huygens carried a functioning microphone to capture the sounds of entry as it plunged through Titan's thick, mysterious atmosphere. This was the first ever audio of a probe entering an alien world's skies. The microphone recorded the faint whine of wind resistance rising from the perfect silence of space, capturing the subtle soundscape as the atmosphere grew thicker and denser. The probe's journey through Titan's air picked up changes in wind and pressure, with the audio shifting from brief, sharp noises to a soft, almost steady hum as Huygens got lower. On the way down, the spacecraft sailed through layers of orange smog, floating particles produced by chemical reactions in Titan's methane-rich sky that shroud the moon in a deep haze. The microphone caught shifts in sound as the probe pushed through these layers, helping scientists map out Titan's complex atmosphere. After filtering out electronic static, engineers transformed the raw audio into a continuous recording, letting researchers link pitch, loudness, and pattern changes to specific altitudes and atmospheric conditions. Titan's air, made up mostly of nitrogen with plenty of methane and other hydrocarbons, is more than 50% denser than air on Earth's surface. Because sound moves more easily in denser gases, these data helped researchers measure Titan's atmospheric properties, like how thick it is and how fast sound travels. The audio confirmed that whines high above Titan's surface were surprisingly gentle, moving just a few meters per second, far less than many experts had guessed. When Huygens finally touched down, its microphone captured the brief impact, followed by the vibrations as the probe settled on Titan's mysterious surface, a combination of ice and dark hydrocarbon-rich grains. These precious data, paired with landing photos, revealed a bizarre world shrouded in haze but brimming with surprises. The sound of Huygens's descent and landing didn't just deepen our understanding of Titan's weather and surface, it set a precedent, showing future missions just how powerful audio could be in exploring the atmospheres of alien worlds. The data Huygens collected during its descent was meticulously combined with readings of temperature and pressure, building a precise vertical profile of Titan's unique atmosphere. By tracking the probe's speed as it drifted downward, scientists could accurately calculate atmospheric density layer by layer. What made this data set truly exceptional was how the sounds captured by Huygens's microphone were perfectly synchronized with these other measurements, adding a valuable layer for cross-checking the atmospheric analysis. This approach of using audio alongside traditional sensors proved to be a powerful way to confirm and validate findings, offering insights that will be incredibly useful for future missions to distant moons with thick atmospheres. Before Huygens ever reached Titan, researchers ran laboratory experiments using chambers pressurized and filled with gas mixtures like those found on Titan. They placed microphones identical to Huygens's inside and observed how sound moved and echoed under different conditions. These acoustic tests let scientists predict what the probe would hear, and when it descended through Titan's skies, the real audio matched expectations with impressive accuracy. This success proved how non-traditional instruments, like microphones, can give a completely new perspective on alien worlds, detecting changes in wind, gauging air density, and even helping to identify things like atmospheric storms or volcanic eruptions. The idea of using sound to study distant planets or moons was once untested, but Huygens showed it could be a game changer. Understanding how sound travels through an alien atmosphere is important, not just for science, but for practical mission design. Future robotic explorers, possibly working in teams, will need to communicate and operate smoothly. Knowing the strengths and quirks of sound transmission on Titan will help engineers design reliable communications and even rotor blades for aerial vehicles, such as the upcoming Dragonfly rotorcraft. Huygens' descent and landing, buffered by Titan's dense air and a tandem parachute system, was gentle and slow, touching down at less than 5 meters per second. Its microphone picked up the sharp thud of impact, then quickly faded into silence as Titan's calm air stilled all motion. For about 70 minutes, the probe continued to send data, including its final sound recordings, before communication with Cassini faded as Saturn's immense bulk blocked the link. This rare audio of a probe drifting into the atmosphere of another world provided an irreplaceable treasure for scientists and a real-time taste of another world for humanity. It became a cornerstone demonstration of what sound-based sensing can reveal, inspiring new ideas for similar experiments on other planets with dense air like Venus or Neptune's moon Triton. Every world offers its own acoustic mysteries, dictated by its unique temperatures, chemistry, and atmospheric thickness. But Huygens proved that microphones can handle even the most extreme environments. The story of Huygens' descent, transformed from raw sound into a living scientific record, remains a key example featured in planetary science education. The data forms part of a growing reference collection, refining calibration methods, and inspiring the next generation of interplanetary instruments. Thanks to this pioneering mission, sound is now recognized as a powerful new sense for exploring alien atmospheres. Titan itself is especially fascinating because of the way its high air density and weak gravity combine. With surface gravity at just about 14% of what we feel on Earth and air, that's 1.5 times as thick as ours. Titan is the only world known where it would be possible for a human with the right set of flexible wings and a protective suit to actually glide or fly. Engineering studies and wind tunnel tests show that even a modest effort like running and flapping arms clad in custom wings could be enough to create real lift on Titan. The heavy air and slow fall combine to make flight much easier than on Earth. Does a resistance and support offered by Titan's thick atmosphere amplify every movement? Not only does this open up imaginative possibilities for visitors, but it makes Titan the ideal stage for experimental flying robots. NASA's bold Dragonfly mission, an 8-rotor drone designed to leap and explore large swaths of the moon's surface, is now on track to test these possibilities for real, bringing dreams of flight on another world closer than ever before. Dragonfly, NASA's ambitious rotorcraft, is designed with multiple propellers perfectly tuned for Titan's dense nitrogen-rich atmosphere. These specially built rotors will make flying on Titan not just possible but highly efficient. Thanks to Titan's thick air and weak gravity, Dragonfly will be able to hop great distances across the surface while using far less energy than any drone could on Earth. Each leap will allow it to explore widely varied terrain, soaring over dunes, skimming across icy plains, navigating ancient craters, and even surveying the mysterious shores of Titan's methane seas. With so much lift from the thick air and so little gravitational pull, the energy required to stay aloft or change locations is remarkably low. This means Dragonfly won't have to crawl over the surface. It can literally jump from site to site, opening up rapid, flexible, and low-risk exploration. Titan's environmental advantages don't stop at easy flight. Because of the dense atmosphere, falling objects plummet slowly. Terminal velocity is much lower than on Earth, reducing the impact of landings and making parachutes almost unnecessary. Robots and modules can be dropped gently with minimal protective gear, dramatically lowering the chance of damage. On top of that, since everything weighs less, about 1/7 of what it would on Earth, robots can carry more equipment or operate for longer stretches, further extending the reach and duration of every mission. Advanced lightweight tools can do heavy-duty science, boosting efficiency and letting researchers get more data per mission. Titan's thick, smoggy air provides another benefit: outstanding protection from harsh solar and cosmic radiation, as well as from micrometeoroid strikes. Electronics and delicate instrumentation can operate on Titan's surface with less shielding, simplifying designs and reducing weight. Unlike Mars or our own moon, Titan's natural atmosphere is a built-in shield, making the moon much safer for long-term robotic and possibly one-day human operations. With flights so easy and surface conditions so forgiving, Titan is the perfect candidate for advanced vertical exploration. Drones like Dragonfly can gather samples and measure wind temperature and chemistry at various altitudes as they zip through the sky. These flights will return the most complete picture yet of Titan's climates, seasonal changes, and clouds. Over time, Fleets of aerial explorers could map out the landscape, track weather in real time, and closely investigate features that ground rovers or landers just can't reach. Above all, the ability to move effortlessly above land and lakes will transform Titan into a dynamic, ever-evolving field site, bringing explorers closer to unlocking the secrets of this bizarre world. If we look further into the future, Titan's friendly environment could offer unique opportunities for humans as well. The low gravity and thick atmosphere make movement easier and reduce the life support requirements for pressure suits. It's almost as if Titan was made for flight. One day, astronauts equipped with winged suits might soar directly over the moon's dunes and lakes, exploring freely as never before. Titan's skies aren't just for drones. The super-dense atmosphere is perfect for lighter-than-air craft, such as scientific balloons or airships, which could float for weeks or months, gathering panoramic images, monitoring weather systems, and analyzing trace chemicals. Instruments slung beneath such crafts could hover at just the right altitudes to collect valuable data and take ultra-stable readings, while the slow winds would make for remarkably steady observation platforms. Sound also travels extremely well through Titan's thick air, enabling new types of communication and navigation. Drones and landers could use sonar to sense landforms, avoid hazards, or even search for geological activity underground, turning Titan's natural acoustics into a powerful scientific tool. Altogether, Titan shines as one of the best worlds in the solar system for both robotic explorers. Someday, human visitors. Few other places combine so many rare advantages: easy flight, soft surface landings, natural shielding, and nearly endless opportunities for discovering the unknown. Technologies proven on Titan, like rotorcraft and balloon-borne labs, could lay the groundwork for future missions to other fog-wrapped or thickly atmosphered worlds. As Dragonfly gears up for its journey, Titan draws the curiosity and effort of scientists everywhere, and its alien skies are set to become a playground for discovery and invention. Farther from Saturn, another surprise waits: an enormous invisible ring that escaped notice until just a few years ago. Discovered in 2009 by NASA's Spitzer Space Telescope, observing in infrared, the Phoebe ring ranks as Saturn's largest and faintest ring. It's so diffuse and spread so far from the planet, stretching from about 6 to 16 million kilometers, or more than 200 times Saturn's radius, that it would span an area larger than 2 full moons in Earth's sky if we could see it. But the ring's particles are so sparse and dark, reflecting almost no sunlight, that only infrared telescopes picking up faint heat from warmed dust grains could detect it. What's remarkable is that the Phoebe ring orbits far outside Saturn's main rings and sits at a tilted angle, matching the strange backward orbit of the moon Phoebe. This moon loops around Saturn in the opposite direction of the planet's rotation, its path constantly bombarded by debris from meteoroid impacts. Over countless years, those impacts launched dust and tiny particles into space, creating a vast, invisible torus that follows Phoebe's odd orbit around Saturn. The Phoebe ring is immense in size, with a vertical thickness up to 40 times the radius of Saturn itself, but its density is so low that all its material combined would barely make up a modest asteroid. Still, its subtle influence is felt throughout the Saturnian system. One of Saturn's mid-sized moons, Iapetus, features a dramatic two-tone appearance, with one hemisphere coated in dark material and the other left bright and clean. The likely culprit, the Phoebe ring. As dust spirals inward under sunlight and radiation pressure, it slowly drifts and rains down onto moons like Iapetus, darkening one face while leaving the other untouched. This marks a rare case where an invisible ring's impact shows up directly on a moon's surface. Phoebe itself is a shadowy, irregular object, probably captured from the Kuiper Belt or another distant part of the solar system. Its carbon-rich makeup and backward path set it apart from Saturn's native moons and explain why the Phoebe ring doesn't match the composition of Saturn's main rings. As fresh impacts continually send debris flying off Phoebe, the ring is renewed over time, never static, always changing. By studying the Phoebe ring, scientists gain a deeper understanding of how space erosion, impacts, and external forces shape not only irregular moons but also the rings around giant planets. The ring's unique tilt and vast reach highlight that Saturn's rings aren't flat or simple. They stretch above, below, and beyond, forming a breathtakingly intricate 3D system. Discoveries like this remind us that there may be other, even fainter rings waiting to be found, not just at Saturn, but orbiting giant planets elsewhere in the universe. Each new faint ring or shadowy band expands our sense of what's possible, turning every fresh perspective into a chance for yet more cosmic discovery. Future telescopes may be able to spot rings like Phoebes around exoplanets, either by picking up their faint infrared glow or by noticing subtle changes as they block starlight during a planet's transit. The Phoebe ring acts as a key example for scientists, showing how these enormous ghostly rings behave even when they're too faint to see with visible light. Despite its low density, the Phoebe ring has a real impact. It plays a role in how mass is shuffled around Saturn's outer system, influences the orbits of distant moons, and even interacts subtly with Saturn's magnetic field, all without ever being directly visible. Its ongoing study reveals just how complex Saturn's extended ring system truly is. When people imagine Saturn's rings, the idea of vast, thick bands sweeping through space comes to mind. But in reality, the main rings, labeled A, B, and C, are incredibly thin, sometimes just 10 meters to a little over a kilometer thick, depending on the region. This wafer-thin structure means that when Saturn's equinox comes and sunlight shines directly through the rings from the side, the rings nearly disappear from view. During these rare alignments, subtle phenomena come into the spotlight, like vertical ripples and mountains in the rings, some towering up to 2 or 3 kilometers high. They aren't solid mountains, but rather clusters of particles raised skyward by the pull of nearby shepherd moons. These ripples and the razor-sharp shadows they cast were captured in detail during the 2009 equinox by Cassini, revealing hills and ridges that identified the complex gravitational interactions shaping the rings. The Moonpan, a tiny shepherd just 35 kilometers wide, orbits inside the Encke gap in the A-ring and exerts enough gravitational force to sculpt vertical and horizontal waves in the ring material. A similar effect comes from Daphnis, which orbits within the Keeler gap, each moon carving out distinct repeating patterns. Resonant alignments with even farther out moons also stir up vertical waves, amplifying small forces until entire swaths of the rings are pushed upward or downward, stretching for hundreds of kilometers. Cassini mapped dozens of these undulating features, shedding light on the collective behavior of orbiting ice and rock. Thanks to the ring's thinness, scientists can track even faint forces that nudge material up and down. Tidal forces, electrical effects, and collisions all play their part, causing vertical changes from just a few millimeters up to kilometers. In the denser B ring, such variations get dampened, but in lighter regions like the C and D rings, structures are free to oscillate. By measuring the shadows of these features and the way sunlight passes through the rings at different angles, scientists can create intricate three-dimensional maps of ring layers, revealing how particles settle and shift. These insights allow researchers to use Saturn's rings as a kind of laboratory, studying the same dissipative, dynamic processes that also shape young planetary systems around distant stars. During equinox, another spectacular change happens. Because the rings are so thin, the famous Saturnian disks can virtually vanish from sight as the sun hits them edge-on. These events, happening roughly every 15 years, turn the bright rings invisible against the darkness of space until vertical structures and faint shadows briefly reappear. Cassini's equinox images not only redefined what we know about ring thickness, but also sparked new questions about their age and stability. If natural collisions and clustering tend to thicken the rings, why are they still so flat? The persistent slenderness hints at constant renewal, possibly supporting the theory that Saturn's rings are either young or replenished by ongoing sources. The way the ring thickness changes with angle also affects how opaque they look, depending on your viewing point. Scientists use observations of stars passing behind the rings, stellar occultations, to measure how much starlight is blocked, revealing the vertical particle distribution and showing whether larger particles congregate in a flat disk or are mixed more randomly. These variations help explain the ring system's hidden dynamics and evolution. The mountains and ripples aren't fixed either. They shift as moons pass by, orbits change, and as external forces act on the whole system, hinting at a living, ever-changing structure. Cassini's detailed photos even captured another rare phenomenon: spokes, which are dark, fleeting streaks that race across the rings during these brief alignments. They're caused when sunlight charges fine dust particles, making them repel each other and temporarily rise above the ring plane, only to settle back down a few hours later. Most common in the B and C rings, these spokes reveal another layer of complexity, showing how gravity, electric forces, impacts, and even sunlight itself all leave their mark. Saturn's rings, with their dynamic vertical structures, countless ripples, and constantly shifting scenes, serve as a powerful analogy for the birthplaces of planets around other stars. Many of the same physical forces seen in Saturn's rings also shape forming protoplanetary disks. Thanks to the treasure trove of data from Cassini's 2009 equinox campaign, modelers are still making new discoveries, teasing out fresh patterns and updating our understanding with ever sharper computational methods. One final astonishing process is known as ring rain. Over time, tiny bits of ice, dust, and even organic molecules slowly spiral inwards from the rings towards Saturn. They don't just drop like pebbles. Instead, their paths are guided along Saturn's powerful magnetic field lines, creating an invisible cascade that falls mainly at the planet's equator. This rain is made up of charged, microscopic particles gently pulled down by electromagnetic forces, which are especially effective for grains smaller than a micron. Cassini and the Hubble Space Telescope have both observed these subtle flows, which can deposit up to 45 tons of material on Saturn every second. Where the ring rain falls most intensely, Saturn's upper atmosphere reveals strange chemical fingerprints, unusual patches with higher water, oxygen, and organic content than the planet's own internal processes would suggest. This ongoing deposit tweaks not only Saturn's chemistry, but also its electricity, shifting how radio waves move and generating electric currents in the upper atmosphere. Cassini even tracked variations in radio signals where ring rain meets the atmosphere, helping map the zones of interaction. The flow of ring rain changes the electrical properties of Saturn's ionosphere and also stirs up the energy balance in the thermosphere, altering how heat is absorbed and radiated away. These never-ending exchanges between rings and planet prove that even the most beautiful features in our solar system are active, interconnected, and continually evolving. This slow, steady ring rain doesn't just alter Saturn's atmosphere, it creates pockets of warmth, shifts in wind circulation, and unique clouds high above the planet's cloud tops. It acts almost like an internal version of how the solar wind shapes Earth's upper atmosphere, but here, Saturn's own rings are the source. As this gentle drizzle of particles continues over time, it gradually eats away at the ring system. The steady loss of mass means Saturn's glorious rings are not permanent. If erosion keeps up at the current rate, they could vanish in less than 300 million years, underscoring the idea that Saturn's main rings are relatively young in cosmic terms. The ongoing dissipation is fueled not only by the inward drift of dust, but also by impacts on inner moons and collisions within the rings themselves, all of which create smaller, more maneuverable grains that spiral down towards Saturn's atmosphere. The dead ring, the innermost and faintest, is particularly vulnerable. Its particles are easily swept up by the planet's magnetic field and funneled towards the atmosphere, serving as a sort of gateway zone between the rings and Saturn itself. The actual makeup of these raining particles tells a story about the chemical history of the rings. Compounds such as tholins, complex organics forged by exposure to ultraviolet light and cosmic rays, show up in the falling material, suggesting a long history of chemical processing in space. When these altered particles finally settle onto Saturn, they could deliver prebiotic molecules, potentially seeding the upper atmosphere with the kind of chemistry that sparks new molecules. Scientists are now recreating these conditions in the lab to see exactly how ring rain might rewrite Saturn's atmospheric chemistry. Remarkably, this drizzle is not uniform. Its intensity changes whether Saturn is an equinox or solstice. When the rings are edge-on and receive the least sunlight, charging slows and rain tapers off. In contrast, during solstice, sunlight is stronger, charging up the particles and increasing the magnetic pull. leading to much heavier precipitation. These fluctuations tie the process directly to Saturn's orbit and its seasons. Cassini even observed brief, unusual auroras, distinct from those caused by the solar wind, triggered by bursts of ring rain. Special ultraviolet glows flared exactly where the influx was greatest, proving Saturn's rings don't just decorate the planet, they play a real physical role in shaping its sky. Mass spectrometers on board Cassini broke down the ingredients in rain detecting everything from ionized water and oxygen to a surprising mix of hydrocarbons. The amount of water alone is enough to adjust the chemistry and even the heat balance in Saturn's upper layers. These findings prove beyond doubt that the rings are not just a pretty backdrop, but are actively woven into the story of Saturn's changing atmosphere. No other planet's rings seem to interact with their host in the same way. Jupiter, Uranus, and Neptune have rings, but lack the same dense, stormy ballet of dust, electricity, and chemistry that unfolds at Saturn. Only here do all the pieces, thick rings, close proximity, and a dynamic magnetic field come together so perfectly. As scientists refine advanced 3D plasma and particle models, they're mapping how even the tiniest charge grains move under Saturn's influence. These electromagnetic footprints could one day help future missions track the ring-atmosphere connection in real time, opening a new frontier in monitoring giant planet weather. Saturn's extraordinary ring rain stands as a perfect case of how something as delicate as drifting dust can leave an outsized mark on the climate and chemistry of an entire world. It's a vivid, continuous exchange that shapes both Saturn's past and its future, shifting from the invisible dance of ring particles to something massive and unmistakable. Saturn's North Pole is home to one of the solar system's most bewildering wonders, the colossal, nearly perfect hexagon. This stable, six-sided cloud pattern stands over the North Pole, with each straight side stretching about 13,800 kilometers, longer than Earth's own diameter. There's enough room inside this strange polygon to fit 4 entire Earths. First noticed by Voyager in 1981, and later observed in stunning detail by Cassini, the hexagon has captured scientific curiosity ever since. Unlike typical jet streams that spiral as wavy ribbons around a planet, Saturn's North Pole boasts a jet stream so organized that it forms a geometric hexagon. The winds inside this boundary reach dizzying speeds of about 320 kilometers per hour, circling the pole at nearly 78 degrees latitude. At the center spins a gigantic vortex reminiscent of a monstrous hurricane, complete with a well-defined central eye, yet hundreds of times larger than any storm on Earth, and totally anchored in place by the pole itself. Researchers believe the hexagon emerges from complicated interactions between Saturn's swirling atmospheric bands. When the speeds and positions of these zonal winds hit just the right balance, fluid instabilities create standing waves. In rare situations, these standing waves become locked into polygonal shapes. Amazingly, laboratory experiments with spinning fluids have even recreated similar shapes under controlled conditions, proving that nature can create geometry out of chaos when the parameters are just right. What's truly astonishing is just how steady the hexagon remains. Over decades of continuous observation, from Voyager all the way through Cassini's orbit, the hexagon has barely budged, even though Saturn's atmosphere is fast-moving and usually turbulent. The central vortex, with its thick, towering cloud walls, stands in sharp contrast to Earth's fleeting hurricanes. Saturn's polar hurricane is permanent, wider than 2,000 kilometers, and sustained not by warm seas but by Saturn's unimaginable atmospheric power. The hexagon also changes its appearance with the seasons. In the darkness of Saturn's long polar winter, the hexagon glows bluish-gray, while the approach of polar summer brings golden hues as sunlight triggers the formation of hydrocarbon hazes. Saturn's photochemistry responds to light, coloring and thickening the clouds above the hexagon, and making it a visible marker for seasonal change. The hexagon's central region is measured to be warmer than its surroundings. Thermal readings suggest this difference may actually help keep the jet stream locked in its shape, isolating and preserving the giant pattern year after year. Further research shows the hexagon has no twin at Saturn's south pole, where only a round vortex is found. This dramatic asymmetry hints at subtle differences in Saturn's atmosphere, wind patterns, or internal heat flow. Scientists are still searching for a clear answer. The jet stream forming the hexagon soars high above Saturn's visible clouds, stretching 300 to 500 kilometers upwards. Modeling this multi-layered wind remains a challenge, but it stands as a perfect testbed for the physics of rotation, turbulence, and planetary symmetry. The hexagon's influence extends well beyond what our eyes can see. High-altitude haze and aerosols trace out hidden motions and reveal that the structure impacts layers far above the main cloud deck. Detailed, multi-wavelength imaging from Cassini captured these patterns for more than a decade, chronicling changes in color and thickness, but always returning to the same striking six-sided symmetry. There is simply no other weather phenomenon like it on any other world, a planetary mystery that endures, mesmerizing both scientists and space enthusiasts alike. As the Cassini spacecraft continued its journey through Saturn's rings and magnetic bubble, it picked up an entirely unexpected sensation: tiny, high-speed impacts from dust grains whizzing along at up to 120,000 kilometers per hour. These collisions didn't just tell a story about the ring's structure and the harshness of space. They became a kind of cosmic soundtrack, marking every encounter as Cassini dove deeper into the heart of Saturn's realm. As Cassini journeyed through Saturn's system, it moved through clouds of microscopic dust, grains so tiny they were often smaller than a wisp of smoke, yet traveling at mind-boggling speeds of over 120,000 kilometers per hour. When these high-speed particles slammed into the spacecraft, they created shock waves that were immediately captured by Cassini's sophisticated instruments. The Radio and Plasma Wave Science (RPWS) device, originally intended to study Saturn's electromagnetic fields and plasma, also turned out to be a remarkably sensitive detector for these mechanical impacts. Each tiny dust collision created a fleeting voltage spike in the RPWS antennas, which once processed produced sounds, sharp pops and crackles, that offered a dramatic real-time audio portrait of Cassini's adventure through space dust. These impacts weren't just for show, they held a wealth of scientific value. The grains Cassini encountered came from a wide variety of sources: icy fragments chipped off Saturn's rings, particles shot out in plumes from Enceladus, and even interplanetary or interstellar dust zipping in from beyond the Saturnian system. Some were the battered remains of micrometeoroids smashing into the rings. Others were ejected from active geysers on moons. As Cassini passed through different territories, the frequency and energy of these hits changed, helping researchers map both the density and possible origins of dust throughout the Saturnian neighborhood. The relative speed of collision was tremendous. Even a microscopic grain carried so much kinetic energy that it could create a significant electronic disturbance in Cassini's systems. Larger particles registered as long, deep spikes in the audio, while tinier grains left brief but sharp bursts. By analyzing the length and strength of these signals, scientists could estimate the distribution and sizes of dust grains, building a detailed model of Saturn's dynamic dust environment. This technique was especially helpful in dark or murky regions, where cameras were blind, making acoustic sensing an invaluable tool for navigating and understanding the rings, plumes, and dust clouds. Cassini's real gift wasn't just data for scientists. It offered something visceral and engaging to the general public. When the electrical signals from these impacts were converted to sound, people could actually hear the spacecraft's passage through invisible storms of particles. This approach transformed abstract science into an experience, letting listeners imagine the spacecraft's journey as it dashed through clouds of dust, every crackle representing a collision between human technology and ancient cosmic debris. Some of these audio recordings have even been remixed into music or turned into immersive learning tools, weaving art and science together to tell the story of Saturn's complex environment. The dustiest encounters happened when Cassini passed near Enceladus or through Saturn's dense ring plane, especially during flybys of the moon's active plumes. The rapid-fire crackles in the recordings clearly lined up with spikes in visual and chemical data, proving plume activity beyond any doubt. During its audacious grand finale, when the craft plunged into the gap between Saturn and the faint D ring, Cassini ventured into unexplored space. To everyone's surprise, The actual number of dust impacts in this corridor turned out to be far lower than anticipated, suggesting a region clearer than models had projected. This result was confirmed by the near silence in the audio, underscoring how real-world data can sometimes overturn expectations. Cassini didn't just detect dust from Saturn, though it also picked up the occasional micrograins that came from totally different origins. Some were traced to passing comets or even interstellar space. This made Cassini not just a planetary explorer, but a valuable outpost for cosmic dust science, adding planetary context to data collected back on Earth. But the story of these high-speed impacts isn't only about space weather and particle mapping, it's also about engineering. Every impact, no matter how tiny, chipped away at the spacecraft's shielding and electronics. By studying the pattern and severity of these hits, mission designers gained crucial insights for building tougher, safer probes. The lessons learned will guide the next generation of missions through hazardous, dusty regions, such as planetary rings, comet tails, or moon plumes. The ability to hear, space through electronic feedback proved especially useful in places where traditional viewing failed, deep inside shadowed rings or thick atmospheric hazes, where even the best cameras couldn't see. Techniques developed by Cassini's team could inspire similar dust and impact detectors for future missions venturing into low-light environments. The RPWS didn't only record dust strikes, it also picked up radio noise, plasma waves, and electromagnetic events. By aligning dust impact data with magnetic field readings, scientists found that dust storms sometimes matched up with sudden changes in Saturn's magnetosphere, suggesting a close relationship between ring materials and the planet's electrical environment. Cassini's ability to layer observations from many instruments made it possible to connect details across the entire Saturn system. Some of the most striking dust recordings came during the mission's final plunges between Saturn and its rings. Sometimes the soundscape was almost silent, other times it was filled with bursts, evidence of micro-ringlets or temporary dust clouds invisible to ordinary instruments. These rich audio datasets are still being mined for both scientific trends and for creative projects that help more people connect with the excitement and complexity of Saturn exploration. Cassini's Dust Symphony stands as an unforgettable legacy, a reminder that what looks peaceful and serene from afar is actually an untamed realm of constant high-speed collisions. Those crackling pops are the soundtrack to one of the most energetic regions in our solar system, where technology meets the cosmos in a dance of discovery. Beyond dust, Saturn itself is a giant stage for electrical storms and auroras. Cassini revealed that the planet is alive with lightning storms thousands of times more powerful than any on Earth. These titanic disturbances unleashed intense bursts of radio waves known as Saturn electrostatic discharges, or CDs. First noticed by Voyager, CDs were studied in depth by Cassini, revealing flashes that last only milliseconds but can outshine all other radio signals in Saturn's huge magnetic bubble. Lightning storms, some lasting hundreds of days, like the great convulsions of the 2010 Great White Spot, produced a symphony of explosive radio bursts, enabling scientists to probe storm structure, depth, and energy. The lightning's roots were pinpointed deep within Saturn's thick, ammonia-rich clouds. Convective currents clashing ice crystals together generated immense electrical charge separations, just as on Earth, but on a far vaster and more powerful scale. Saturn's auroras are another dazzling display, swirling, shifting bands of light around the poles, captured by Cassini's infrared and ultraviolet eyes. But unlike Earth's auroras, which are triggered mainly by solar winds, Saturn's involve a dance between solar particles, the planet's dynamic magnetosphere, and plasma contributions from its rings, and most notably Enceladus. When Saturn's moons, especially Enceladus, inject charged particles into the magnetic environment, it triggers waves of plasma that spiral along Saturn's magnetic field lines, lighting up the planet's upper atmosphere with brilliant colors. These auroras don't just pulse with the sun, they're directly influenced by Saturn's rotation and the positions of its moons, forming a living, ever-changing electric system on a planetary scale. Cassini's suite of sensors unraveled these mysteries in concert, painting Saturn as a world where electricity, plasma, dust, and magnetism are in constant play, an environment both unpredictable and breathtaking. always ready to surprise. Cassini's sensitive magnetometer and plasma wave instruments gave scientists an unprecedented way to listen in on Saturn's magnetic realm. As the spacecraft sailed through Saturn's magnetosphere, it detected a rich variety of plasma waves, everything from slow-moving alphon waves and swirling ion cyclotron oscillations to rapid electron plasma pulses. These signals didn't just vary at random, they pulsed and changed in time with Saturn's rotation, with the movements of the rings, and even when the planet was blasted by storms from the sun. By continuously mapping and analyzing these patterns, researchers were able to reconstruct the architecture of Saturn's invisible magnetic field, noticing that, unlike other planets, Saturn's field is shockingly well aligned with its axis of spin. This perfectly lined up field remains a puzzle, defying standard dynamo theory that expects at least a small tilt. Even after years of Cassini data, only minute fluctuations were found, hints that Saturn's deep metallic interior is locked in an intricate electrical dance with the outer layers. It's in this electrically charged theater that Saturn's rings literally hum to the planet's tune. Cassini discovered that not only are dust and ice particles within the rings shaped by gravity, they're constantly playing with Saturn's electric and magnetic environment. Charged grains, especially the finest powders, can levitate above the ring plane when the sun charges them through ultraviolet light, forming mysterious seasonally changing spokes. These spokes flicker in and out depending on sunlight angle, connecting each fleeting pattern to the planet's larger electromagnetic heartbeat. Lightning storms on Saturn, with their massive radio bursts, send radio signals spiraling through the magnetosphere, signals Cassini could hear and use to track the positions and strengths of those storms, turning radio astronomy into a powerful weather tool. Cassini also flagged dramatic magnetic field reversals and rapid current sheet crossings, events triggered by the turbulent push and pull between Saturn's magnetic bubble and powerful gusts from the sun. In these moments, the whole magnetic landscape could shift, a process reminiscent of the explosive reconnection events that power space weather back on Earth. Each encounter gave clues about how Saturn's gigantic electric system is shaped by internal and external pressures, and revealed that the entire planet acts as a linked, living conductor. Even satellites like Enceladus left electromagnetic wakes, regions of enhanced electric current trailing behind their orbits, marking out the moon's hidden influence on the surrounding space. All of these records, taken together, transformed Cassini into a floating node in Saturn's electric symphony, where lightning, plasma waves, auroras, and the rhythmic swirl of rings and moons play in a single, interconnected performance. Changes in the regularity of magnetic signals hinted at exchanges and interactions deep inside Saturn, possibly between the metallic hydrogen core and the swirling overlying layers, giving a rare glimpse of the planet's mysterious interior. This system, where lightning outbursts, ring spokes, radio waves, and electrical currents all feed into one another, stands as one of the most complex and fascinating cosmic networks humans have measured. Turning from the electromagnetic concert to the visual poetry of Saturn's rings, Cassini's close-up views revealed another kind of record: spiraling density waves that ripple across the rings like grooves cut into a vinyl record. These fine, tightly packed patterns are born from the gravitational pulls of nearby moons, especially the unique twin satellites Janus and Epimetheus. Whenever a ring particle's orbit aligns with a certain ratio to the orbit of a moon, it's given a subtle but repeated tug. Over time, these nudges stack up, creating spiral ridges that wrap around the planet. Each wave spreads like a sound wave through the ring's icy particles, with its spacing controlled by the mass of the responsible moon and the density of the ring region. Janus and Epimetheus, which effectively swap orbits every 4 years, are the masters of this orbital tug-of-war. But when they change places, the gravitational pattern changes too, and the spiral waves reset, moving to new locations. In this way, the rings become a living calendar. Their grooves a permanent diary that records each cosmic step and swap. Cassini could read the date and history of these dances simply by measuring the distance between wave crests. By studying the width and height of the spirals, researchers could even infer the physical properties of the rings themselves. their density, stickiness, and how energy ripples through their particles. Other moons like Mimas, Tethys, and Dione also leave their fingerprints, not only sculpting density waves, where particles clump side to side, but also vertical bending waves, which lift and drop particles above and below the ring plane. These overlapping signatures create complex, beat-like interference patterns, letting scientists reconstruct a real-time map of the entire Saturnian system, even where moons themselves are too faint to spot directly. In many places, density waves split, intersect, or branch, evidence of multiple moons competing for gravitational dominance. During Saturn's equinox, the sun shines directly along the ring's edge, casting shadows that reveal the three-dimensional structure of these ridges. Cassini's images showed that some crests tower up to tens of meters tall, confirming the vertical nature of these waves, and giving scientists a new ruler for measuring changes in ring density, moon position, and orbital migration. Time-lapse images and models could even track the slow tidal drifting of moons over millions of years, as the grooved patterns shift along with their gravitational sculptors. The richness of the ring patterns at Saturn is unmatched in the solar system. Each crest, ripple, or spiral records a physical event, an orbital encounter, a meteorite strike, a transient disturbance. By mapping these features, Cassini opened a new chapter in orbital archaeology, reading the rings as a natural archive, tracing back the battles and dances between Saturn, its moons, and its own deep gravitational pulses. These spiral diaries are, in essence, the dynamic signatures of celestial interactions, preserving clues to Saturn's inner structure, its moon's migrations, and the way whole solar systems might evolve around other stars. What looks like mere decoration from afar is, in fact, a living, shifting record of the universe's ongoing story. Every spiral wave winding through Saturn's rings holds a record of its orbital past and the ever-changing forces in play, thanks to Cassini's extraordinary data. With unprecedented clarity, scientists can now read these spirals, unraveling stories about how Saturn's rings and moons have interacted across time, and using them to unlock broader mysteries about disks, rings, and planetary physics throughout the cosmos. But the rings host more than spiral waves. Cassini also revealed a family of bizarre small-scale features in the A-ring. The propellers, unlike the sweeping spirals carved by major moons, these tiny aircraft propeller shape disturbances are the handiwork of moonlets only a few hundred meters across, far too small to spot directly, but large enough to make their presence felt. As these hidden bodies orbit through the icy swarm, their gravity shifts the paths of nearby particles, leaving behind a central gap trailed by symmetrical S-shaped wakes, like a miniature jet plane etched across the rings. The most famous example, nicknamed Blairia, sprawls nearly 8 kilometers long and has been tracked for years, showing subtle changes in position and shape as it responds to shifting local environments. Even though the moonlet at its core is invisible, its effect spans the ring in a clear signature, an unmistakable indicator of an unseen intermediate world between single ring grains and full moons. Propellers like Blairia are fossils of the ring's evolution, likely leftovers from Saturn's earliest days, or fragments left when bigger bodies broke apart. Cassini found more than 150 such propellers, especially in the A-ring's mid-region, where conditions are just right, dense enough to stabilize their structures, but not too crowded to erase them by collision. These delicate imprints survive for months, sometimes years, making them perfect markers for scientists investigating the properties of the ring's fluid. Each propeller tells researchers about the mass, density, and even the stickiness of ring material. By tracking how quickly their gaps close, researchers gauge how easily ring particles flow, or if they linger, how strongly they cling together. The propellers themselves are likely loose piles of icy rubble, formed by gentle collisions over time. Their loose structure makes them both tough, able to withstand gentle nudges without shattering, and modest in their gravitational pull, able to carve disturbances, but not dominate entire swaths of the ring. Over time, these little moonlets may collect more material and grow, or be worn away depending on their neighborhood in the rings. Some have been seen to drift slowly across the ring, possibly following gradients in ring density, or due to subtle asymmetries in particle flow, showing that not only do the rings move, but so do the tiny worlds within them. Cassini's timing was perfect. During Saturn's equinox, when sunlight grazes the ring's edge on, some propellers cast measurable shadows, revealing their vertical relief, sometimes rising dozens of meters above the flat ring plane. Shadows confirmed models of how big and tall these structures really are, providing a three-dimensional view of what was previously only an abstract signal. The patchy distribution of propellers, with some regions teeming, others nearly empty, also teaches astronomers where ring conditions permit their formation and survival. Mapping their locations helps reveal the balance of forces that keep parts of the ring quiet enough and stable enough for propeller wakes to persist, away from the chaos of powerful moon resonances. Altogether, the presence and behavior of propellers show that Saturn's rings aren't a simple smooth disk. Instead, they're a mosaic of interactive living structures shaped by objects both visible and hidden, on scales ranging from dust particles to moonlets. But the surprises don't end with the propellers. Cassini's camera zoomed in on Saturn's small moons Pan and Atlas, which stunned scientists with their bizarre shapes, neither round nor simply lumpy, but resembling flying saucers or plump ravioli. The secret is Saturn's rings themselves, Pan orbiting within the Encke gap of the A-ring, and Atlas just outside the main ring edge, continually sweep up ring particles as they travel, collecting the fine material along their equators. Over time, this persistent bombardment builds up thick, smooth ridges around their midsections, while the rest of the moons remain relatively flat. The result is like a dumpling, with a distinct raised collar of ice, unique in the solar system. Pian is about 35 kilometers wide, and thanks to Cassini's close flybys, its equatorial ridge was imaged in high detail, a perfectly smooth arc several kilometers tall, wrapping the moon like a belt. Atlas, slightly smaller, sports a subtler, more diffuse ridge, probably because its environment is less crowded, or the pace of ring accretion is different. Both moons have such low gravity that ring particles can stack up loosely, never getting squeezed down or mixed into the interior, so the new ice remains as a fresh, glowing surface layer. These strikingly smooth ridges appear almost unmarked by impacts, suggesting that the process of gathering ring material is ongoing or at least very recent. This delicate balance of gravity, ring particle flow, and orbital dynamics lets Pan and Atlas clear gaps in the rings as they orbit, while simultaneously accumulating the ring material that gives them their distinctive look. The age of their ridges is probably quite young when compared to the moons themselves, showing that Saturn's rings and moons remain a dynamic, evolving system even today. The peculiar shapes of Pan and Atlas highlight what happens when external processes, like constant snowfall from surrounding rings and a touch of centrifugal force, overpower the slow tug toward a spherical shape. Most worlds round themselves out as they grow under gravity, but these moons are too small and their environment too active for that rule to apply. Instead, we get natural sculptures, icy ravioli, forever orbiting in the midst of Saturn's sparkling rings, living proof that planetary systems can operate on every scale and still surprise us with new forms right before our eyes. At Saturn's poles, the story takes a dramatic turn. Unlike the smooth equatorial bands wrapped in icy ridges by ring material, the polar regions of Pan and Atlas show rugged terrain pocked with tiny craters. This contrast hints that while the poles are ancient, marked by eons of impacts, the equators are constantly rebuilt by fresh deposits from the rings. It's a natural experiment in regional resurfacing, where environment, not just internal geology, sculpts a body's face. The implications are far-reaching if such equatorial bulges can grow around small moons in Saturn's rings. Similar processes might shape forming worlds in the swirling disks around newborn stars. Local accretion along the midsection could alter both the final shape and spin of planets, making Pan and Atlas small-scale previews of planetary formation in action. One lingering question is how stable these ridges really are. Built up from loosely packed ice, they might be vulnerable to collapse or erosion. A passing meteoroid, an unexpected tidal tug, or shifts in electrostatic charge could destabilize the ridge. Although Cassini's visit clocked no dramatic changes, Longer observations may one day catch a ridge as it shifts or sheds material. Another curiosity is how these added equatorial bulges alter the way Pan and Atlas tumble through space. With extra mass loaded at their waists, their moment of inertia changes, potentially adding small wobbles or vibrations as they orbit. Studying such subtle motions may one day reveal hidden details about their inner structure and density, offering a new way to probe the insides of worlds too small for seismic instruments. Pan isn't just shaped by the ring, it leaves its own signature on it too. As it glides through the Encke gap, Pan's gravity stirs up delicate edge waves, creating soft ripples that ripple outward through the gap's icy border. These undulations are direct evidence of Pan's mass, and serve as a live demonstration of how even modest moons can engineer ring structure, as surely as ring material shapes them. Atlas, although not powerful enough to carve wide gaps, still perturbs nearby ringlets. In these close environments, even the smallest masses can leave a fingerprint, as Cassini's precision imaging lays bare. The ravioli shapes of Pan and Atlas challenge all the old assumptions about small moon morphology, showing that an object's form can be defined as much by its neighborhood as by its own gravity and geology. By watching these moons in detail, Cassini gave scientists a unique window into the mechanics of body formation, accretion, and surface evolution in particle-rich environments, insights that ripple outward to our understanding of planet birth across the universe. As Cassini's historic mission neared its end, the spacecraft went bold, diving through the mysterious gap between Saturn and its innermost D-ring in a series of daring grand finale orbits. Mission planners braced for danger, predicting a violent zone packed with dust and debris shed from the inner rings. To prepare, Cassini turned its high-gain antenna into a protective shield and readied its instruments to measure every dust collision in real time, expecting a chaotic barrage. What happened next defied all expectations. As Cassini slipped into the gap, the sensors found an unexpected oasis. The corridor was almost completely free of dust. The anticipated storm of impacts never materialized. Instruments that once had crackled with dust signatures now remained eerily quiet, confirming that the region between the D-ring's edge and Saturn's atmosphere was much cleaner than any model had predicted. Instead of a gradual tapering of particles, Cassini found a sharp, abrupt border separating the sparse gap from the faint D-ring itself, forcing scientists to rethink the ring's dynamics and the forces at play. So why was it so clean? One idea is that electric and magnetic forces at the ring's edge sweep dust outward, while radiation pressure evokes a natural cleaning effect near the planet. Rather than particles spiraling inward in great numbers, they seem to be actively repelled, leaving this corridor relatively empty. With this new knowledge, Cassini could relax its defensive protocols, enabling high-resolution measurements that would have been impossible in a debris field. This zone turned out to be the perfect vantage point for the mission's final investigations. Cassini's clean corridor led to a scientific windfall. Free from the interference of dust, Cassini's gravity and magnetometer instruments delivered pinpoint readings of Saturn's internal structure and rotation. The magnetometer mapped the planet's magnetic field closer than ever before, shedding new light on its deep interior. The mass spectrometer NMS could directly sample the upper atmosphere, detecting molecular hydrogen, water vapor, and various hydrocarbons, yielding the sharpest atmospheric data from Saturn in history. These finds rewrote the book on theories about ring decay and the transport of material earlier models, assuming inward leakage of dust and debris, simply didn't match reality. Instead, Saturn's D-ring turned out to be thinner and more sharply bounded, with very little particle leakage detectable between it and the planet. The stability of this clean corridor suggests Saturn's rings may be more long-lived and stable than previously thought, perhaps existing in a state of dynamic equilibrium rather than slowly fading into the planet. It's a phenomenon echoed in the disks around distant stars where planets and magnetic effects carve similarly clean paths. Cassini's experience has become a blueprint for mission planners. Sometimes the highest risks reveal the safest routes, and direct exploration is the surest way to revise our models. Yet the rings that appear so solid and smooth from afar are anything but. Up close, Cassini revealed that Saturn's rings are a bustling, three-dimensional swarm of icy particles, ranging in size from tiny grains to great boulders several meters across. Each particle orbits Saturn on its own, following a subtly different path determined by its distance from the planet. What we see as a ring is actually a dense, dynamic river of particles, more like rush hour traffic than a continuous ribbon or disk. In fact, there's far more open space between particles than ice itself. Cassini's cameras and instruments showed these ring particles in constant interaction, colliding, bouncing, clustering, and even jostling apart as they circle Saturn at dizzying speed. Although their movement is fast, their actual collisions are surprisingly gentle, measured in centimeters to meters per second. This never-ending ballet creates turbulence and shear, especially in the densest regions of the rings where collisions are most frequent. The motion of each particle is affected by its precise orbit. Those slightly closer and zip around faster, those farther out drift behind, establishing a perpetual traffic jam that gives rise to the intricate patterns, clumps and gaps Cassini saw in such stunning detail. The peaceful banded beauty of Saturn's rings dissolves, up close, into a wild arena of icy chaos, one that is always in motion and always reshaping itself before our eyes. The poles of these moons display a patchwork of rougher terrain and scattered small craters, pointing to older planetary surfaces at the extremes. Meanwhile, their equatorial regions are actively shaped by material from Saturn's rings. This stark geological split suggests that resurfacing happens in specific zones. The ancient poles and younger ring-fed equators together hint at how moons can be rebuilt from the outside in. The abrupt equatorial ridges hint at how satellites might form within thick, dusty disks. In young planetary systems, we might see similar sculpting happen as new worlds coalesce from swirling material. When matter gathers along a spinning object's equator, it can reshape that body's look and even change how it spins over time. The modest moons Pan and Atlas are living laboratories for planetary growth, a scaled-down preview of how much larger worlds might have emerged. They show that a body's shape can be determined by outside influences just as much as by its own interior. One puzzle scientists still debate is just how stable these ridges really are. Their loose structure, combined with the moon's weak gravity, suggests they could be eroded or collapse over time. Micrometeor strikes, the pull from Saturn's gravity, or even electrical charges might disturb these fragile ridges. Hall. Cassini's data didn't catch any major reshaping, but that doesn't rule out long-term change. Future missions, keeping watch for years or decades, could see how these ridges evolve. Their mass at the equator also slightly shifts each moon's balance, potentially causing faint wobbles or vibrations as they move. This could be a window into how their interiors are arranged. Studying such tiny variations in spin and movement may reveal secret layers or density patterns within. Pan is especially remarkable in how it interacts with the edge of Saturn's A-ring. Its gravity stirs up gentle waves along the nearby ring gap, creating graceful ripples through resonance. Direct, visible proof of its pull. These edge waves don't just trace Pan's mass and orbit, they show a constant give and take between moon and ring. Pan not only sculpts the gap, but is itself sculpted by its surroundings. It's a feedback loop woven deeply into Saturn's ecosystem. Atlas, for its part, doesn't carve out a major gap, but does send similar patterns through surrounding ringlets. Its smaller mass means it can't maintain an open space, but it still stirs the particles nearby, showing that even the tiniest objects can leave lasting marks. Cassini's close camera work made these subtle patterns visible for the first time. The odd shapes of Pan and Atlas make us question old assumptions about how small moons develop. They remind us that surface features aren't always the product of underground forces, where a body sits and the environment around it can be just as critical. Saturn's smallest satellites now play outsized roles in refining our theories about how moons and rings interact, evolve, and last over time. Their seemingly whimsical shapes turn out to be rich historical records written by their ongoing dance with Saturn's rings. Construction of these ridges was just one revelation. As Cassini entered the final phase of its mission in 2017, it took a daring path, diving repeatedly between Saturn and the edge of the D-ring through a gap scientists had never explored. The expectation was a curtain of dust and debris, requiring the spacecraft to shield itself carefully. Instruments were set to measure the barrage of particles in real time, and for the first leap, Cassini's main antenna served as a makeshift shield. The team braced for chaos. What actually happened was almost the opposite. Cassini glided in silence through this narrow region, encountering hardly any dust at all. Instruments that should have crackled with collision data instead recorded peace and quiet. The radio and plasma wave sensor, designed to capture the faintest pings of incoming dust, registered virtually none. Where scientists had predicted a hazy, dangerous transition, they found a stark boundary between the end of the rings and the upper atmosphere, a space cleaner than anyone imagined. Why was this? Models had long predicted that the innermost D-ring would trail off, gradually seeding the inner region with fine particles. Faint rings and scattered light hinted at continuous leakage, but Cassini's real-world measurement upended that rather than a gentle taper. The transition was sharp and very little debris had crossed it. The theories soon shifted. Maybe electromagnetic fields, or Saturn's own magnetic shield, push charged dust away. Maybe sunlight itself helps keep the zone clean, or tides and gravity sweep particles outward. Whatever the cause, this clean corridor let Cassini continue its daring dives without heavy protection. On subsequent orbits, engineers could take more scientific risks, running sensitive instruments like the magnetometer and ion mass spectrometer at full power. This dust-free gap became a prime location for detailed study. Whole folds. With no clouds of grit-clogging sensors, Cassini mapped Saturn's gravity, magnetic field, and atmospheric makeup better than ever before. Magnetic readings revealed fine details about Saturn's inner workings. The mass spectrometer tasted untainted samples of the atmosphere, measuring hydrogen, water vapor, even the signatures of heavier elements, data nearly impossible to capture through a dusty fog. The surprise clean zone wasn't just a lucky break. It forced scientists to rethink how material migrates in rings, how fast they erode, and how stable they might remain over millions of years. What looked like a slow decay from ring to planet turned out to be a much more constrained process than anyone thought. The D-ring examined up close was thinner and fainter than expected, its inner edge cleaner, with fewer waves or new clumps migrating across the gap. Some small disturbances appeared, possibly echoes of hidden influences, but most particles stayed put. So Saturn's rings might last longer and change more slowly than previously imagined. This also echoed findings from more distant systems, where planets and magnetic fields shape empty spaces within dusty disks around other stars. Saturn's ring gap became a model for how dynamic forces can create open pathways, not chaos or turbulence between more crowded regions. This lesson in exploration mattered for Cassini and for future missions. Never just trust models or assumptions. Real-world data can overturn even widely accepted theories. Saturn's hidden clean corridor turned fear into opportunity, letting the mission perform extended close passes and gather unrivaled data to the very end. Sometimes, it turns out, the most important discoveries are what you do not see. From a distance, Saturn's rings look like smooth, solid sheets of ice. The reality is far more complex. The sprawling, ever-changing clouds of countless particles, from fine dust to rocky boulders meters across. Each one circles Saturn on its own path, their orbits crisscrossing in a gravitationally ordered chaos. Cassini's sharp eyes watch these countless fragments bounce, collide, and slide past each other, more like moving crowds than still surfaces. The speed differences between inner and outer particles create gentle turbulence and shear, especially where the rings are thickest and busiest. There's far more empty space than solid material in any patch you pick. Saturn's rings aren't the tranquil bands they seem from afar. Their beauty comes from their restless, dynamic complexity. Saturn's rings create a dynamic world of colliding ice and dust, constantly in motion. Most ring particles are made up of water ice, but their purity varies, some gleaming white, others tainted by dust or organic material. These differences in composition lead to noticeable shifts in brightness and color across the rings. Cassini's instruments confirmed that especially farther from Saturn, the ice is cleaner, while closer to the planet, the grains pick up more contamination, dulling their glow. Despite their solid look, even the thickest rings are mostly empty space. Their overall density is so low that it's less than a sheet of paper spread over each square meter, making Cassini's daring dives between the rings and Saturn surprisingly safe. From Earth, or through Cassini's camera, the illusion of solidity comes from countless particles reflecting sunlight at once. But zoom in, and it's easy to see that the rings are a transparent lattice of shifting particles, each one tracing its path around the planet in a sprawling swarm. The A, B, and C rings differ in how bright and opaque they appear, with the B ring holding the most mass, but all share this granular construction. Clumps and gaps appear and disappear all the time. Tiny self-gravity wakes, temporary strings of particles lightly bound together, leave fleeting streaks and textures. Cassini's radio and stellar occultation experiments, passing signals through the rings, gave scientists cross-sections of this structure, exposing hidden density variations and tiny gaps. This revealed a richly layered ring system, with light scattering through the spaces, especially in the less crowded C and D rings. When Saturn is at equinox and sunlight shines edge-on, tall shadows stretch across the rings, letting researchers calculate their vertical thickness and layering. Gravity sculpts these particles into ever-changing formations. Small clumps will gather for a moment, then break apart under the constant bombardment of collisions and tidal forces. In thick regions, gravity can line up particles into radiant streams or wakes, quickly forming and dissolving as they orbit, a pattern Cassini was able to spot up close. These dynamics are so similar to flowing sand or grains on Earth that scientists use some of the same fluid-like models, adapted to account for all the particles bouncing off each other. But here, the viscosity, the resistance to flow comes from physical collisions, not internal stickiness. This mathematical treatment helps explain how ring edges sharpen, how gaps are maintained, and why waves and spirals ripple outward after big disruptions. Saturn's rings rise just 10 to 100 meters tall, but vertical motion is present. Some particles bounce up or down, especially when prodded by the gravitational pull of moons in tilted orbits. Cassini spotted vertical waves and ripples stretching for thousands of kilometers, vestiges of old impacts or ancient nudges from nearby worlds. Even with all this chaos, the rings display breathtaking order. Each sharp gap matches an orbital resonance with a moon, meaning particles in those locations are synchronized, pulled out of place, or shepherded by the moon's steady gravitational tug. This cosmic choreography keeps the rings tidy despite constant collisions. Tiny impacts from cosmic dust grains wear away the icy fragments, breaking some apart, darkening surfaces, and creating a constant drizzle of fine powder into the rings. Over time, this acts as a recycling mechanism, gradually aging the rings and feeding new materials into the flow. And the story isn't just about gravity. Electrostatic charges develop, especially as sunlight strikes, making the smallest particles repel or even levitate above the ring plane. Cassini observed spokes, dark, ghostly lines formed by charged dust, further proof of an electromagnetic dance within the rings. Throughout Cassini's extended stay, repeated passes over the same regions let scientists witness the ring's evolution in action. Dense clumps drift, others unravel, and features that once seemed permanent changed within just a few years. Saturn's ring system is far from a static belt. It's a restless, ever-evolving ballet. Shifting to Saturn's night side, the planet reveals another hidden spectacle in infrared light. Unlike the cold of space, Saturn glows in darkness, shining with internal warmth captured by Cassini's thermal cameras. This invisible light comes from two main sources: leftover heat from the planet's birth, and an ongoing process called helium rain, where helium sinks within the deep hydrogen atmosphere, releasing extra energy. All this makes Saturn emit nearly twice as much energy as it takes in from the Sun. Cassini's infrared spectrometer mapped this soft glow and discovered that the planet's heat isn't distributed evenly. Warm belts wrap around the equator and polar hotspots remain visible, even at night. As Saturn tilts through its long seasons, sunlight disappears in some regions for years. Yet these areas still shine in infrared, slowly warming even before the sun's return, thanks to internal heating. This allowed Cassini to trace jet streams, watch the famous North Polar hexagon emit heat, and track big weather systems without waiting for sunrise. Infrared images didn't just clarify Saturn itself, they revealed how rings and moons cooled after plunging into shadow during eclipses. The fastest cooling parts lost their heat almost instantly, telling Cassini that the particles were small and porous, with low thermal inertia. Dense ring sections, such as parts of the B ring, held onto warmth just a bit longer. These temperature differences told scientists more about the makeup and size of ring material. When a star passed behind Saturn, Cassini's instruments used the starlight's faint dip in infrared, shining through the planet, to map changes in the atmosphere at different heights. This occultation method drew temperature profiles and revealed layers of winds, haze, and turbulence. During Cassini's daring final dives, direct measurements from inside Saturn's upper atmosphere confirmed what the infrared maps saw from afar. Temperatures were warmer than expected, forcing scientists to revise their models of atmospheric heating and circulation. Tiny fluctuations in the global thermal glow even hinted at what lay far below, providing potential clues about Saturn's interior and possible upwelling currents from its deep core. By combining this thermal imaging with fresh data on gravity and magnetic fields, Cassini helped refine the blueprint of Saturn's inner structure, offering one of space exploration's best glimpses inside a gas giant. Altogether, Cassini's thermal discoveries prove that both Saturn and its rings are far more lively, variable, and rich with physical phenomena than ever imagined. A world where even the quiet darkness glows with secrets. Some of the most intriguing patterns revealed by Cassini's thermal eyes were tied to powerful atmospheric waves and massive storms, while others were driven by Saturn's seasonal cycles. By repeatedly scanning the planet's night side, Cassini captured a real-time movie of Saturn's ever-changing weather and climate. The glowing warmth that beamed from Saturn's surface at night wasn't just a static map, it was a living record, carrying hints of shifting jet streams, brewing tempests, and environmental transitions. This steady internal glow stood in stark contrast to Saturn's rings, which remain colder and give off much less infrared radiation. In Cassini's composite images, Saturn's disk often blazed with hidden heat, while the great rings hovered like ghostly shadows, emphasizing the fundamental difference in how energy flows through the planet versus its rings. Saturn's heat is largely internal, a legacy of the planet's own formation and helium-driven currents deep within, while the rings shine only with borrowed sunlight. Cassini's ability to jump between visible and infrared imaging allowed scientists to locate features invisible to the naked eye, pinpointing storms by their heat signatures, tracing subtle jet streams and following temperature boundaries as they moved across the globe. This dual approach opened entirely new windows into Saturn's meteorology and structure, transcending what traditional cameras could see. It also highlighted the fact that Saturn isn't alone. Jupiter also radiates internal warmth and has been mapped by other missions, but Cassini delivered our sharpest, most complete view yet of this night shine phenomenon. In the broader quest to understand gas giants, the detection of invisible heat confirmed that these worlds are not just passive balls of gas. They are energetic, churning, and still evolving long after their birth. On Saturn, though, night is never truly dark. Even when the sun drops below the horizon, the world is softly illuminated by ring shine, the wash of sunlight reflected off the thousands of kilometers of icy rings floating above. The effect is much like the way our moon lights up Earth at night, but on a gigantic planet-wide scale. The rings act as a colossal, scattered mirror blanketing Saturn's night side in a subtle silvery twilight. Cassini's cameras caught this phenomenon time and again, especially during the planet's long polar nights when sunlight was absent for years at a time. The brightness of ring shine shifts with the orientation and tilt of the rings. When they're open and catch the most sunlight, their reflected glow is intense enough to cast shadows on the night side and reveal cloud shapes and motions, providing scientists with a form of passive night vision for atmospheric studies. The B and A rings, being denser and cleaner, reflect more light than the dimmer, dustier C and D rings, but every band contributes at least a little glow. Ring shine is more than just a pretty effect. Its strength depends on the ring's purity and structure, so Cassini's instruments measured how the glow changed to infer subtle details about ring composition. Clean, icy sections threw back bright twilight, while more contaminated or dusty patches produced dimmer ring light, providing yet another way for scientists to probe the rings without touching them. This phenomenon isn't unique to Saturn. Jupiter's moons, for example, get a muted version of the effect from sunlight reflected off their planet's clouds. Still, Saturn's vast, brilliant rings make the effect far more powerful and spatially variable. The result is an environment where constant ring shine shapes both the look and chemistry of the planet. Over time, the gentle illumination may even influence the chemistry of Saturn's upper atmosphere, driving slow but ongoing reactions that would otherwise only happen by day. This subtle, eternal twilight showcases how rings help shape not only the physics but the chemistry of their world. For future explorers, ring shine could prove invaluable. A soft, continuous glow from the rings means landers or probes on Saturn, or even its moons, would rarely face complete darkness, making it easier to operate science instruments or navigate during the planet's endless nights. Understanding how ring shine varies across time and location will help teams design better missions and could give explorers a source of natural low-level light in one of the solar system's most mysterious environments. On a deeper level, ring shine is a poetic reminder. Saturn's rings are not just ornaments orbiting in isolation. They are active, influential players, feeding light and energy to their host planet, leaving a delicate, measurable mark on everything they touch. The twilight they create is a fusion of science and beauty, billions of tiny ice fragments scattering sunlight into an observable phenomenon, turning Saturn's long nights into phases alive with texture and quiet, luminous activity. As Cassini neared the end of its historic journey, the mission's focus shifted from discovery to responsibility. In 2017, engineers executed a carefully planned final act, sending Cassini on a controlled dive into Saturn's atmosphere. This wasn't just for poetic closure. It was to prevent Earth microbes from ever contaminating Saturn's potentially habitable moons, especially Enceladus and Titan, both worlds with ingredients that might support life. Cassini made close flybys through Enceladus's water geysers, detecting organic molecules and signs of heat beneath its ice. With such tantalizing evidence, preserving the moon's natural conditions became vital. Leaving a derelict spacecraft in Saturn's system would be too risky. Sooner or later, gravity or orbital decay could bring Cassini crashing onto an untouched moon, delivering hardy Earth microbes and inadvertently contaminating a pristine world. To address this, Cassini's final weeks were devoted to precise, fuel-saving orbits that lined the spacecraft up for a guaranteed dive into Saturn itself, a destination sure to destroy any life on board and leave no trace behind. The last moments were dramatic. As Cassini plunged deeper, it continued transmitting data, streaming back real-time details about Saturn's temperature, composition, and magnetic fields until atmospheric friction and heat destroyed the instruments and silenced the signal forever. This ecological farewell was the product of evolving space ethics. Over the decades, planetary protection rules have tightened as our knowledge of places like Enceladus and Titan has grown. The idea of forward contamination, the possibility of introducing Earth life to other worlds, demands that explorers become careful stewards, not just visitors. Even with cleanroom assembly and spacecraft sterilization, it's impossible to eliminate every microbe, meaning a direct impact on an ocean moon could compromise all future searches for alien life. By crashing purposefully into Saturn, Cassini left these environments untouched, ensuring that future discoveries will be that much more credible, untainted by the fingerprints of a previous visitor. The mission's finale required meticulous planning. Cassini needed just the right amount of fuel for its last maneuvers, a carefully timed engine burn, and a calculated entry angle that would maximize the return of science data and guarantee destruction. Its final signals, fading as the spacecraft was swallowed by Saturn's atmosphere, were relayed to Earth and marked the end of a 20-year odyssey. For scientists and engineers, saying goodbye to Cassini was deeply emotional. Many had devoted decades to its successes, and its discoveries forever changed our understanding of Saturn and its family of moons and rings. The controlled sacrifice closed the mission with meaning and integrity. Not a funeral, but a final selfless act, in service of science and the preservation of possible alien worlds. Cassini's ending set a new standard. Future missions to places like Europa, Ganymede, or Enceladus will build in similar end-of-life safeguards. In space, as on Earth, our responsibilities continue to grow. Cassini's story became one of respect, curiosity, and care, a model for how to explore boldly while honoring the hidden life we might one day discover. Right up until its last moments, the spacecraft's journey was guided by rigor, foresight, and wonder, making its final act a fitting farewell to the world it revealed. Cassini's grand finale transformed the risk of contaminating an alien world into an act of profound scientific respect. This ending wasn't just about shutting down a spacecraft. It was about guaranteeing that the search for life on Saturn's moons would remain untainted and believable. By sacrificing itself in Saturn's atmosphere, Cassini ensured that future missions, but also our own hopes for true discovery, stayed credible. When we eventually send robotic explorers to drill, scoop, or dive below the ice of these distant moons, we'll know what we find is authentically Saturnian, not a trace of Earth carried accidentally across the void. Cassini's final moments burning up in Saturn's golden clouds turned it from a mere observer to a part of the planet revealed, leaving behind nothing but transformative data and a narrative of careful exploration. That sacrifice guarantees both a legacy and a renewal, the future of planetary science protected, and the mysteries of Saturn kept pure for the next generation of explorers. Among Cassini's most dramatic discoveries was Saturn's South Polar Hurricane, an immense and complex storm system unlike almost anything else in the solar system. Spinning directly over the South Pole, this hurricane revealed all the familiar elements of a terrestrial cyclone: a well-defined eye, a towering eye wall, spiraling cloud bands, and a deep central vortex. The resemblance to storms on Earth was stunning, except for scale and cause. Saturn's hurricane remains fixed over the pole, unmoving in latitude, and is fueled not by warm ocean water, but by the planet's own internal heat and immense atmospheric convection. The size alone is staggering. The calm eye stretches more than 2,000 kilometers across, dwarfing any hurricane known on Earth. Around that eye is a swirling wall of clouds rising over 30 kilometers above the surrounding landscape, with winds in the eye wall measured at a fiercely persistent 500 kilometers per hour, faster than any hurricane ever seen on our planet. High-resolution images from Cassini revealed internal layers of swirling motion, a swirling eye of the storm in both optical and infrared wavelengths. Despite all its power, however, this storm isn't driven by the rapid heating and cooling cycles that energize hurricanes on Earth. There are no oceans. Its energy comes from within. Saturn's constantly escaping heat, coupled with dynamic vertical updrafts. The forces holding it in place are equally unique: Saturn's rapid rotation and the peculiar pull of the Coriolis effect trap, the storm directly at the pole, creating a stable anchor point where opposing flows spiral together in a long-lived vortex. Unlike traveling tropical cyclones, this hurricane hardly shifts, anchored in Saturn's deep fluid atmosphere by planetary dynamics. Thermal cameras aboard Cassini showed that the cyclone had a genuinely warm core, a region of higher temperatures at its center, a feature rare among giant planet storms, where most vortices are cold at the core. This warm center hints at upward-moving heat from the depths, feeding the storm's massive updrafts and keeping it spinning over decades. The storm's eye and its vertical stack of clouds made it a towering pillar in Saturn's meteorological system. Cassini also found a host of other smaller vortices dancing nearby, swirling mini-cyclones that sometimes merged, sometimes circled the main hurricane in patterns that echoed laboratory fluid dynamics experiments on Earth. This towering storm became a natural demonstration of how planetary atmospheres organize themselves under extreme conditions. Optical images revealed encircling cloud bands around the hurricane, rotating at different speeds and interacting through intricate wave patterns. By carefully tracking how these changed with the seasons and different lighting, Cassini captured a kind of time-lapse view of the storm's behavior, illuminating changes in vertical structure, density, and sunlight penetration. Unlike mid-latitude regions, Saturn's poles are free from the alternating jet streams found closer to the equator, which means the polar vortex can maintain its symmetry and power without being torn apart by turbulent crosswinds. The persistence of this storm is remarkable. For over a decade, Cassini watched its size, shape, and internal motions remain nearly steady, varying only in subtle cloud textures and brightness. This stability points to a finely tuned atmospheric balance, an environment where opposing forces operate in harmony to sustain a megastorm for years on end. It's a demonstration of the extraordinary equilibrium that can exist in the deep atmospheres of gas giants, providing a kind of window into weather on planets without a surface. The South Polar Hurricane is also a fascinating counterpoint to Saturn's other great polar feature, the famous North Polar Hexagon, a geometrically perfect six-sided jet stream that surrounds the North Pole. Each pole, it turns out, hosts massive, strikingly organized atmospheric systems. These features, when compared with Jupiter's more turbulent, ever-changing Great Red Spot and polar vortices, highlight Saturn's uniquely calm yet powerful circulation patterns. Cassini's suite of instruments dug even deeper. Evidence pointed to the storm reaching far below the cloud tops, possibly down into the lower stratosphere. Its vertical reach and the way it churns up different atmospheric layers offer vital clues about how heat and chemicals move through Saturn's thick skies. Interestingly, despite its mighty winds, Cassini detected no lightning in the polar hurricane. This sets it apart from storms elsewhere on Saturn and on Earth, where charge separation and electrical discharges are common. It suggests important differences in how storms build up energy, and perhaps how different gas giants generate and lose electrical charge in their atmospheres. While the hurricane was centered at the pole, Cassini also recorded some of the fastest winds in the solar system howling elsewhere on Saturn, particularly along the equator. Here, jet streams reach mind-bending speeds up to 1,800 kilometers per hour, world records for planetary atmospheres. These broad east-west bands are similar to Earth's jet streams in direction, but surpass them in both speed and width by orders of magnitude. The equatorial jets are symmetrically distributed on either side of the equator, a rare arrangement among the gas giants, and remain surprisingly steady through time. Cassini's repeated observations revealed that these powerful winds don't just skim the clouds' tops, they extend deep down into the planet's atmosphere, indicating a tightly knit system linking surface-level weather to interior dynamics. The stability and vertical depth of these flows sets Saturn apart from other planets, both in terms of meteorology and planetary structure. The absence of solid ground lets the atmospheric layers slide over each other with far less friction, leading to smooth, high-velocity currents and persistent striped patterns in Saturn's visible clouds. Even high latitudes away from the equator host alternating bands of eastward and westward flow, though these narrower currents are slower and more variable. Yet, the overall unity and stamina of Saturn's jet streams gave Cassini an unrivaled opportunity to study weather on a scale and speed unmatched anywhere else. Seasonal changes affected some of the bands, but the essence of Saturn's atmosphere remained rock-steady across years, offering a powerful natural laboratory for planetary science and fluid dynamics. Cassini's wind measurements brought new precision to these studies, providing a library of profiles at different heights, latitudes, and changing times, a record that will inform and inspire models for years to come as we continue to decipher the secrets beneath Saturn's swirling clouds. Cassini's detailed wind data revolutionized the study of planetary atmospheres, giving scientists a chance to test and refine models of how gas giants circulate heat and energy. The powerful, relentless jet streams prove that Saturn's atmosphere, despite appearing gentle and uniform in visible light, is actually a showcase of extreme physics and dynamic interactions. By capturing wind speeds, measuring the stretch and twist of clouds in fast-moving shear zones, and observing eddies and turbulent waves at the boundaries where jets collide, Cassini provided a window into both weather generation and the fundamentals of atmospheric flow. Data revealed that these invisible highways don't just move air, they help transfer heat, shape storms, and alter the appearance of the entire planet. Jet streams and high winds affect how Saturn releases its interior heat, influence local chemistry, and change cloud brightness and color by aligning ice crystals in neat paths. The spacecraft's visible and infrared cameras, working alongside spectrometers and Doppler measurements, created a complete picture of wind patterns, speeds, and the energy flowing through every cloud deck. These observations showed that even when a planet looks placid, its deeper layers can be roaring with activity. Comparing Saturn to Jupiter and Earth drove home just how unique each world is. Saturn's equatorial winds outpace even Jupiter's fastest jets, while the planet's gentle color bands conceal a power Earth's atmosphere cannot match. Not only are Saturn's winds faster, but their stamina and steadiness over years push the limits of fluid dynamics. Cassini's comparison of wind and storm data across multiple planets helped uncover the deep links between atmospheric flows, internal heating, planetary rotation, and even magnetic effects, the interconnected web that makes each gas giant distinct. Seasonal swings do have some effect. Cassini tracked how Saturn's winds subtly shifted as sunlight moved from one hemisphere to the other across the planet's long 29-year year. These small changes gave scientists clues about how deeply winds penetrate and how much inertia is built into Saturn's gigantic weather engine. It's a slow but telling demonstration of how solar input shapes everything from cloud motion to the planet's climate resistance. Saturn doesn't just have steady winds and jet streams. Roughly every 30 Earth years, it erupts with an enormous atmospheric event known as a Great White Spot. These convective outbursts dwarf any storms seen on our planet, flaring up as blindingly bright, fast-spreading clouds that can wrap around the entire planet in weeks. Cassini's instruments watched the most recent of these superstorms in 2010, tracking its explosive growth from a small, bright patch in the northern hemisphere to a planetary disturbance stretching over 15,000 kilometers. The origins of each great white spot lie deep inside Saturn's atmosphere, where heat slowly builds up beneath stable layers. When the pressure becomes too great, it erupts upward, forming gigantic columns of rising cloud, cooling and condensing into brilliant white tops that reflect sunlight so efficiently they're visible from Earth with small telescopes. Like thunderstorms on Earth, but on an entirely new scale, these storms introduce new kinds of waves and turbulence into Saturn's jet streams, reshaping wind patterns and stirring up enormous vortices that can linger for years after the main event fades. Cassini found that great white spots do much more than just dazzle in visible light. Thermal scans revealed that the storms pump heat all the way to Saturn's upper atmosphere, creating hotspots and long-lasting temperature anomalies. These disturbances affect wind and cloud behavior globally, shifting the planet's climate and leaving a legacy long after the storm itself dissolves. Radio and plasma detectors recorded dramatic bursts of lightning, among the strongest seen anywhere in the solar system, offering proof that water clouds and powerful vertical motion are active deep inside Saturn. The chemical effects were just as striking. Rising columns of air brought up compounds like ammonia, phosphine, and hydrocarbons from deep within the planet, rearranging atmospheric chemistry and providing scientists with a rare peek into usually hidden layers. Each great white spot acts as a natural probe, briefly uncovering Saturn's secrets before receding back into the planet's swirling weather system. After the storm, Cassini watched the aftermath. Dark lanes, cloudless belts, and turbulent swirls carved out by the storm's fading energy, all slowly smoothing out as Saturn's atmosphere returned to its quiet balance. The slow build-up and rare occurrence of these storms is still a puzzle, but most evidence points to a delicate balance between internal heat, a slowly thickening stable layer, planetary tilt, and the timing of solar energy input. The effects of a great white spot reach all the way up to the stratosphere, creating hot zones and wave patterns that ripple through the highest clouds. Cassini's continuous, multi-wavelength monitoring during and after the 2010 storm produced the most detailed dataset ever captured of one of these planetary giants, setting a new standard for atmospheric science. Scientists around the world now look forward to the next event, expected in the late 2030s, hoping future missions can catch even more of the build-up, explosion, and aftermath in real time. Beyond the planet's atmosphere, Cassini also uncovered extraordinary links between Saturn and its icy moons, especially Enceladus. Orbiting within Saturn's powerful magnetic field, Enceladus shoots geysers of salty water and ice grains from its south pole, material that immediately interacts with the magnetic environment. The plumes contain charged particles, ions and electrons, that get swept up along magnetic field lines. This turns Enceladus into a natural electric generator, producing currents that flow between the Moon and Saturn, forming what's essentially a plasma cable stretching across hundreds of thousands of kilometers. Cassini measured these effects with sensitive magnetometers and plasma instruments. Each time the spacecraft passed near Enceladus, it recorded magnetic field changes and plasma surges perfectly matched to the Moon's geyser activity. This direct electrical connection is similar to the interaction between Jupiter and its volcanic moon Io, but uniquely shaped by Saturn's environment and the chemistry of Enceladus's subsurface ocean. These discoveries revealed just how much a small moon can influence, and even help fuel a giant planet's magnetic system. Enceladus wasn't just orbiting passively, it was sending energy, particles, and even hints of its own internal ocean far into space, offering yet another glimpse into the dynamic, interconnected world Cassini explored for over a decade. The plumes erupting from Enceladus don't just create dramatic jets of water and ice, they actually build a vast, invisible plasma torus around Saturn, fundamentally altering the magnetosphere in ways no other moon quite matches. Unlike Jupiter's moon Io, which fills Jupiter's magnetic field with sulfur and oxygen ions from its volcanoes, Enceladus acts as a source for water group ions, such as H, AvO, Alwev, and O, Alwev. This continuous injection gives Saturn's inner magnetic environment a unique chemical profile, with a dominant composition that's directly linked to the Moon's hidden ocean. When these icy plumes blast out through Enceladus's southern fissures, they pass through and interact with Saturn's magnetic field lines. The effect is more than passive. Charged particles in the plumes bend and drape the magnetic lines, creating twists and currents that Cassini detected up close. The degree to which field lines arc and curve around the plume provided direct evidence of ionized conductive gas and plasma, confirming that this moon's outgassing actively sculpts its magnetic neighborhood. This interaction zone, centered on Enceladus's orbit, is continually changing. It intensifies or wanes depending on how powerful the plumes are at any given time. Electrons funneled along these bent field lines are accelerated, generating radio and ultraviolet signals, radiostatic and glowing auroral spots that Cassini's instruments detected and mapped from both close flybys and afar. Notably, radio and plasma wave data picked up field-aligned currents, literally electric currents flowing down Saturn's magnetic field lines, completing a circuit between moon and planet. The effect is so strong and persistent that it influences Saturn's shimmering auroras at the poles. In ultraviolet images from both Cassini and telescopes like Hubble, bright auroral patches repeatedly appeared at precisely the spots where Enceladus's magnetic footprint intersected the planet's atmosphere. This means the electric cable linking moon and planet is not just theoretical. It pulses, glows, and flexes with real energy, lighting up Saturn's polar skies like a cosmic wire. But Enceladus's electromagnetic influence goes even further. Every time the plumes are active, they flood Saturn's magnetosphere with fresh plasma, changing the density, chemistry, and motion of charged particles trapped around the planet. In this way, the tiny icy moon becomes not just a sculptor of space weather, but also a regulator of radiation belts and particle flows. This is critically important for spacecraft safety. Cassini had to calibrate and occasionally adjust its own instruments in response to changing particle environments caused by Enceladus's outbursts. The plumbing for this entire system leads right back to Enceladus's ocean. Water, salts, and organic molecules rising from the warm depths erupt as jets, become electrically charged by sunlight and Saturn's own field, then spiral along field lines, connecting ocean to space in a planetary web of energy and matter. When plumes surge, the electric circuit linking Enceladus and Saturn strengthens, increasing auroral brightness and the local plasma density. When geyser activity declines, the circuit dims and relaxes, a feedback loop where geology drives space weather. This electromagnetic coupling doesn't just light up auroras and change plasma conditions, it actually feeds back into orbital mechanics. The drag produced as Enceladus injects plasma acts a bit like resistance in a circuit, transferring tiny bits of momentum between the Moon and Saturn's field. Over millions of years, this could subtly alter Enceladus's path, proving that magnetic energy can reshape not just atmospheres, but orbits as well. Cassini's flybys were specifically designed to unravel this system. With magnetometers, particle detectors, and radio receivers, the spacecraft captured how Enceladus's activity created magnetic, draping, fluctuating densities, and sudden bursts of energy. Some of these bursts matched what are called magnetic reconnection events, akin to solar flares, where field lines snap and rejoin, releasing pent-up energy in quick, bright flashes. This shows that the electric link is anything but static. It can surge, shift, and flicker on both short and long timescales. In essence, Enceladus serves as a physical and electromagnetic bridge to Saturn, plugging its ocean directly into the planet's powerful field. This circuit shapes not just Saturn's auroras, but also the inner magnetosphere's energy flows, the Moon's own motion, and the radiation environment around both bodies. Cassini's pioneering observations showed for the first time that a tiny geologically active moon could wield such gigantic influence over a planet and set a new benchmark for understanding interconnected planetary systems. Turning to another unique Saturnian dance, the moons Janus and Epimetheus provide a spectacular demonstration of orbital mechanics in action. These two small moons don't just share nearly identical orbits, they actually swap positions every 4 years in a gravitational ballet found nowhere else among major moons. For most of their orbits, Janus circles Saturn just inside of Epimetheus. Being closer to the planet, Janus moves slightly faster, gradually closing the gap between the two. As they approach, mutual gravity comes into play rather than colliding. The moons gently push against each other, exchanging orbital energy. Janus is kicked outward into the higher, slower orbit, while Epimetheus is nudged inward into the lower, faster path. They swap places, then the process reverses after another 4 years, and the cycle repeats. Cassini tracked these swaps with exquisite precision, revealing that the exchange is not just safe, but incredibly stable over decades. The difference between their orbits is only about 50 kilometers, astonishingly close in planetary terms. If you could plot their motions in a rotating reference frame, each moon would appear to trace a horseshoe path relative to the other, never quite overtaking but coming close enough for gravity to flick them into new orbits. As if exchanging seats on a carousel, the swap is made possible because Janus is about twice as massive as Epimetheus, ensuring the transfer happens cleanly and consistently. No actual collision or close call occurs. Their mutual gravitational influence is just enough to redirect the paths smoothly. Although other small bodies in the solar system, like Trojan asteroids, share orbits with planets, no major moons have such an intimate, direct, and observable co-orbital configuration. Janus and Epimetheus, often called co-satellites, provide a living, testable case for celestial mechanics. Cassini's high-resolution imaging and orbital data allowed scientists to confirm theoretical models of this horseshoe exchange and to measure small, real-time changes in the moon's velocities and heights as they switched places. These regular swaps don't cause visible surface changes. The moon's heavily cratered, irregular bodies record a history of impacts, not collisions, but their positions affect how they interact with Saturn's rings and local debris. Lying just outside the main rings, Janus and Epimetheus can subtly steer ring particles, creating faint waves and density patterns at the edge of the A ring. Their predictable orbital dance thus influences not only their own stability, but also the structure and appearance of the edge of Saturn's ring system. By watching these moons, scientists continue to fine-tune our understanding of orbital resonances, migration, and long-term balance, knowledge that helps us interpret similar pairs among asteroids, moons around other planets, and potentially exoplanets with shared orbits. This configuration likely arose naturally as Saturn's moon system settled and evolved. Tidal forces and the gradual transfer of energy brought the moons into a stable embrace that prevents collisions, favoring mutual stability over millions of years. Cassini's sustained observations provided multiple real-world examples of their swaps, supporting and refining our best models. Now, Janus and Epimetheus stand as the most detailed, accessible illustration of large-scale co-orbital motion, giving planetary scientists a perfect, natural experiment in the ongoing dance of gravity and motion. Their constant, measurable orbital interplay is a living demonstration of gravitational mechanics, not just something written in textbooks, but a spectacle playing out before our eyes. Janus and Epimtheus have danced this gravity-driven duet for countless generations, their flawless timing and persistent stability now fully explained thanks to Cassini's detailed tracking. What once seemed a rare cosmic coincidence is now one of planetary science's most illuminating case studies in orbital dynamics, a testament to the subtle power of gravity and the elegance of Saturn's natural architecture. Shifting from orbital choreography to the secrets of an icy moon, Cassini also unveiled the extraordinary tiger stripes of Enceladus. These are not ordinary surface cracks. Running parallel across the moon's south pole, these four linear fractures named Alexandria, Cairo, Baghdad, and Damascus Sulcus stand out for both their size, about 130 kilometers long, evenly spaced, and their dramatic role in Enceladus's geology. Unlike the brittle faults we see on many frozen moons, Enceladus's tiger stripes are dynamic. They are warmer than their surroundings, acting as thermal hotspots in an otherwise frigid world. Using Cassini's infrared sensors, scientists discovered that surface temperatures along these fractures rise to nearly 200 Kelvin, far higher than the expected ambient cold of the moon's icy crust. This concentrated heat means that along these stripes, Enceladus's subsurface ocean has direct access to space. Through these active vents, water vapor, ice grains, and a medley of organic compounds are propelled outward in shimmering jets. Cassini spotted over 100 individual geysers erupting from these fractures, each ejecting material at up to 2,000 kilometers per hour, fast enough for some of it to escape Enceladus entirely and feed Saturn's diffuse E-ring. But these geysers aren't just randomly bursting. Their activity ebbs and flows in sync with Enceladus's orbital position. As the moon swings closer and farther from Saturn along its elliptical path, gravitational tides squeeze and stretch its core. This periodic flexing widens or closes the tiger stripes, driving pulses of venting, most intense when the fractures are pulled most open. At the heart of it all is a globally connected liquid water ocean, buried beneath 20–30 kilometers of ice, and possibly over 10 kilometers deep in places. The tiger stripes act as direct gateways from this hidden sea to the surface, channeling up water that picks up minerals and organic molecules from the seafloor. As it rises through cracks and porous ice, it carries with it a chemical legacy that Cassini could sample directly by flying through the plumes. Cassini's direct plume crossings revealed an extraordinary molecular diversity, water vapor dominated, but with ammonia, methane, carbon dioxide, and crucially organic molecules containing multiple carbon atoms, all signatures of potentially life-friendly chemistry. Of particular interest were silica nanoparticles and hydrogen, material that hints at warm, mineral-rich hydrothermal vents on the ocean floor. The analogy to Earth's deep ocean vents, which teem with life despite eternal darkness, makes Enceladus a top target in the hunt for extraterrestrial habitats. The persistence and regularity of these plumes, seen for decades already and probably ongoing for much longer, suggest an internal engine that can keep the ocean liquid and the vents open. Tidal heating is the likely power source. As Saturn tugs on Enceladus, internal friction generates heat, enabling this active world beneath a shell of ice. The breathing of the tiger stripes helps ensure the ocean doesn't overpressurize. These continuous, steady emissions function as natural relief valves, minimizing the risk of explosive eruptions or sudden, catastrophic breakups of the crust. Over time, this process doesn't just shape the surface frost from returning plume material, gradually coats the region around the stripes, creating one of the brightest and youngest patches on Enceladus, a surface nearly free from impact craters and shining with fresh reflective snowfall. High-resolution photography exposes the complexity, ridges, pits, layered deposits, carved and built by ongoing eruption and frost recycling. Importantly, these massive fractures and their outgassing are not frozen in place. Long-term Cassini monitoring suggests they may migrate or change slowly over time, perhaps as the ice shell thins, the ocean rises, or subsurface stresses shift. Seasonal sunshine plays a secondary, more subtle role, occasionally tweaking vent activity, but it's tidal flexing that sets the rhythm of this internal dance. Cassini's data established the tiger stripes as more than just striking surface marks. They are functional portals between Enceladus's internal ocean and the vacuum of space, channels for water, heat, and complex chemistry to escape and be sampled without ever drilling through the ice. The plumes have offered us a shortcut to the depths, making Enceladus one of the most exciting locations in the search for life beyond Earth. Any future mission to this moon will target these breathing fractures, seeking answers in the vapor columns for both planetary dynamics and the possibilities of living worlds hidden under ice. Now moving to Titan, Saturn's biggest moon, Cassini uncovered another alien wonder: sprawling equatorial dunes made not of silicate sands like those in Earth's deserts, but of solid organic molecules. Vast fields of these dunes cross thousands of kilometers and tower up to 100 meters high. Titan's sandy grains are composed of hydrocarbons such as benzene and acetylene, born not from geological breakdowns but from the ongoing chemical processing of Titan's methane and nitrogen-rich atmosphere. Sunlight and energetic particles transform simple gases into complex aerosols, which rain down, collect, and eventually form a sand of solid organics that piles up to build the planet's dunes. These seas of dark sand stretch across Titan's equator, mostly within the latitudes 30 degrees north and south, favoring low-lying plains where wind and landforms collaborate to trap sediments. Cassini, armed with radar capable of seeing through Titan's thick golden haze, uncovered a network of long parallel ridges running predominantly westward over the moon's vast dark terrain. The patterns resemble those of the world's largest deserts, like the dunes of Namibia or Arabia, showing that certain physical principles of aeolian or wind-driven processes apply on both Earth and Titan, even though the underlying chemistry is utterly different. Wind acts differently under Titan's dense nitrogen-methane air, which is about 1.5 times as thick as Earth's, and provides much more buoyancy for lightweight particles. Though winds are generally gentle, the particles move more easily, so even weak breezes or rare, strong methane storms can push the sand. These slow, persistent migrations explain the regular global distribution Cassini mapped, with dunes marching in symmetry across dark plains and avoiding brighter icy highlands. To low sector taken by Cassini's infrared and visual mapping instruments confirm the dark dunes are dominated by organic molecules, possibly tholins, which are complex materials formed from atmospheric reactions of methane and nitrogen. These findings show that Titan's chemistry flows from top to bottom, with the atmosphere not just shaping weather, but constantly feeding the surface in a slow, steady rain of organics. The dunes themselves cover an area larger than Earth's Sahara Desert, about 13% of Titan's entire surface, and their presence links atmospheric evolution, climate history, and surface geology in one continuous cycle. Altogether, Titan's fields of organic sand stand as proof that alien landscapes can look familiar, even as their chemistry and origins are utterly different from home. With Cassini's data, planetary scientists gain not just images, but a dynamic understanding of how Saturn's largest moon evolves from the atmosphere down, endlessly remaking its landscape out of molecules built in the sky. The way Titan's dunes align tells a story not only of its winds, but of the moon's broader atmospheric engine. Persistent easterly equatorial winds, shaped by Saturn's slow seasonal tilts, push these organic sands into long parallel ridges, their formations stretching across thousands of years. While the great patterns are driven by Titan's unique global circulation, local topography and sporadic wind events can twist the dunes in new directions, leaving behind subtle kinks and bends, just as happens in Earth's deserts. Titan's gravity, only about 1/7 of Earth's, means even gentle breezes can push grains farther, making this low-gravity, high-pressure environment ideal for building and preserving dunes. Erosion is minimal and sand movement is slow but enduring, allowing these reservoirs of organic material to steadily accumulate and persist. The orientation, size, and placement of Titan's dunes aren't random. Instead, they're shaped by an interplay between latitude, elevation, and climate. The dunes cluster in wide, dry equatorial plains, avoiding the polar zones dominated by vast methane lakes. There, high humidity and sticky organics keep sand from drifting, so the poles are almost dune-free. On the other hand, Cassini's radar mapped interdune islands with rougher, brighter surfaces, possible outcrops of bedrock or icy crust peeking through. These barriers redirect the drifting sands, while older, uplifted terrains resist erosion and remain as bright, ancient plateaus surrounded by newer, organic-rich dunes. The way these features fit together, dark, wind-formed dunes abutting bright, ancient ridges, shows in sharp relief how Titan's climate, chemistry, and geology have worked together for eons to shape a diverse landscape. Studying Titan's dunes provides more than just a snapshot of weather and winds. It preserves a deep record of the moon's shifting climate cycles. Changes in dune alignment or length hint at past episodes of stronger storms, different prevailing winds, or drastic climatic transitions. Some abandoned or confused dune fields may even be fossils of ancient wind patterns, much as Earth's desert dunes record Ice Age winds. By unraveling their stories, scientists hope to reconstruct major epochs in Titanian climate. These sands are more than mere geological curiosities. They're a treasure trove for the Dragonfly mission, a nuclear-powered rotorcraft that will someday fly from dune to dune, sampling the grains directly. Dragonfly's landings and onboard laboratory promise to reveal, grain by grain, the chemistry of Titan's organic world, and perhaps the recipes for primitive chemistry that might echo the origins of life. Thanks to Cassini, we know that Titan is the only place in the solar system where complex organics rain from the sky, coat the ground, drift in vast dunes, and persist in a frigid alien cycle. But dune fields are only part of Titan's story. The moon's most Earth-like distinction is the presence of rivers, lakes, and even seas. Though here, the liquid isn't water, but methane and ethane. With a surface temperature around 94 Kelvin, Titan's hydrocarbons exist as flowing, open liquids, forming a complete hydrological cycle like nothing else found off Earth. Cassini's instruments, especially radar and infrared, revealed an astonishing planet-wide network of branching channels, braided rivers, and looping valleys. These river systems carved deltas, canyons, and shorelines, their shapes nearly mirroring the forms of watersheds on our own planet. Methane on Titan is as dynamic as water on Earth. It evaporates into the sky, forms clouds, and returns as methane rain to replenish rivers and fill the great polar lakes. Some river channels are hundreds of kilometers long and display classic dendritic tree-like branching, clear evidence of ongoing weather and long-term surface erosion. At the north and south poles, major rivers empty straight into vast lakes and seas, like Kraken Mare and Ligeia Mare, with Cassini's radar confirming flowing water-carved deltas, submerged inlets, and even canyons over a kilometer deep. The details are strikingly Earth-like, but the mechanics operate on alien terms. Titan's slow gravity, paired with thick air, means rivers flow with little force, maintain narrow, deeply incised channels, and form deltas with muted waves and slow sediment buildup. Wind rarely disturbs the broad, glassy methane seas. As a result, Titan's rivers have high stability, carving, preserving, and refilling ancient valleys with minimal erosion. Cassini's close monitoring recorded not only active rivers, but also fossil channels, ancient, now dry pathways likely to revive with seasonal rains or longer-term climate shifts. Some channels show recent flooding and darkening after suspected storms, suggesting that Titan's climate still experiences dramatic, if rare, weather events. Methane rivers, thus, are living features, some visible, some awaiting the next surge of rain. Why does Titan keep its methane rivers flowing? The atmosphere holds about 5% methane, but sunlight should break it down quickly. Instead, the rivers and lakes constantly replenish what's lost, tying surface geology to atmospheric chemistry in an ongoing loop. Where rivers cut through faults or run across steep terrain, their direction and structure reveal faults and tectonic features, adding another tool for understanding Titan's hidden geologic past. The variety of channels, from permanently flowing streams to ephemeral flood-carved canyons, provides a unique window into the range of geological activity possible in cryogenic landscapes. The formation and persistence of rivers also point towards cycles of climate change driven by orbital shifts or long-period weather. Cassini's decade of observation gave us just a snapshot. The next mission might catch the planet in another mood, seeing rivers run stronger or vanish as the weather shifts over years. Titan's methane rivers aren't just geological. They reshape ideas of planetary habitability. These flows transfer organic molecules, nitrogen compounds, and atmospheric tholins from highlands to lowlands, concentrating and transforming them in ways that could set the stage for prebiotic chemistry. Some riverbeds may be layered with rich organic sediments, natural laboratories reminiscent of ancient Earth, reshaped in a profoundly alien mold. Take the remarkable images beamed back from the Huygens probe's landing in 2005. As it descended, Huygens revealed a flat floodplain dotted with rounded, pebble-like ice boulders, eerily reminiscent of river-worn stones back home. These pebbles bear the hallmark of being transported and shaped by flowing liquid methane, direct evidence that Titan's rivers have the power to move and sculpt its icy landscapes, just as water does on Earth. Huygens, landing in the vast Shangri-La region near contrasting dark plains and bright highlands, finally gave scientists their first eye-level glimpse of Titan's surface. More than 700 images from its brief historic descent revealed a plain marked by signs of an active, weathered, and dynamic world. Titan's rivers, like its dunes, reinforce a vision of an active planet, one where surface, climate, and atmosphere are deeply connected by cycles and flows, all sculpted in substances far different from our own, but ruled by the same physical laws. Thanks to Cassini and Huygens, our understanding of this distant, frozen world is forever changed, and the search for cosmic habitability now extends confidently into the methane-dark rivers and organic sands of Saturn's largest moon. When the Huygens probe touched down on Titan, it offered humanity its very first glimpse of a truly alien landscape, a frozen floodplain strewn with rounded pebble-like blocks. These small objects, mere centimeters across, had the unmistakable look of river rocks. Their shapes, smooth, rounded, and lacking sharp edges, suggested they were sculpted by a history of flowing liquids, much like the stones found in Earth's riverbeds. But on Titan, the water responsible for this work is actually frigid liquid methane, and the rocks themselves are solid ice. Spectral readings confirm that these pebbles were mostly water ice, but their surfaces were darkened by a thin coating of complex organics known as tholins. These organics are born high in Titan's hazy atmosphere, where ultraviolet sunlight breaks down methane and nitrogen, triggering a cascade of chemical reactions. Over time, the resulting tholin particles settle out of the air and blanket the frozen ground, giving everything a muted, rusty color. The result? A landscape that looks strangely familiar but is made of materials utterly foreign to any river delta on Earth. The way these pebbles were arranged, and their rounded contours strongly hinted at long-term fluvial, liquid-driven processes. Moving in slow, methane-rich streams, the icy fragments would have tumbled, collided, and gradually lost their rough edges, each acting as a time capsule sealed by the frost and haze. The pebbles were embedded in darker, fine-grained material, perhaps wet sediments or organic-laden dust, showing signs that the area had once experienced flowing liquids but was now stable, likely in a dry spell between episodic methane floods. Some pebbles even appeared partially buried, suggesting slow but active sedimentation and surface change. The broader riverbed was mapped as Huygens descended. The probe's camera revealed a branching dendritic network of dark, sinuous channels converging toward the landing site, classic drainage patterns created by liquid runoff. While Huygens sensors found no standing liquid at the landing moment, temperature, humidity, and wind data suggested an environment where periods of methane rain and runoff are possible. The lack of a splash or bounce, and the firmness of the landing surface pointed to a cold but solidified riverbed, rather than a soggy or recently flooded plain. At the landing site, the ground temperature was recorded at a chilling 94 Kelvin. In these conditions, water is as hard as granite, while methane can behave like water on Earth, freezing and thawing with the seasons, able to flow and erode the ice beneath. While Titan's fluvial activity might be much slower than what we see on Earth, Over millions of years, the cycles of methane rain, runoff, and evaporation have been powerful enough to transport and smooth pebbles across the moon's surface. Every rounded stone is a tiny record of that cold, slow dance. Later, Cassini's orbital imagery revealed similar terrains all across Titan: river channels, alluvial fans, and extensive networks shaped by ancient or intermittent flows, confirming that what Huygens saw was not unique. The evidence points to a world where river-like processes operate under familiar physics, but with exotic materials and at glacial speed, painting Titan as a remarkably dynamic world shaped by a strange but effective cycle of freezing, raining, and flowing methane. The probe's nearly 72 minutes of post-landing operation returned a treasure trove of data: temperatures, pressures, humidity, and up-close visuals of a world previously hidden in haze. All of it pointed to the same conclusion: Titan's atmosphere, surface, and climate are tightly linked by active cycles of rain and erosion, freezing and thawing, with the rounded pebbles serving as clear proof that liquid-driven processes have molded this surface, just as water sculpts valleys and stones on Earth. This direct evidence from Huygens, paired with Cassini's global perspective, changed the way scientists think about Titan, not as a static, icy husk, but as a lively, evolving world where ancient pebbles and riverbeds tell the story of alien weather and geology. Switching to Saturn itself, the question of why the gas giant shines so brightly in infrared, emitting nearly twice as much energy as it receives from the Sun, has fascinated planetary researchers for decades. Multiple lines of evidence, including observations from Cassini and earlier missions, confirm that Saturn radiates a surprising amount of heat, especially from its night side, which cannot be explained by sunlight alone. This excess heat comes from deep within Saturn's interior. The leading theory centers on a remarkable process called helium rain. Deep inside the planet, pressures and temperatures are so extreme that hydrogen exists in a metallic fluid form. As Saturn slowly cools over billions of years, helium that was once mixed with hydrogen becomes insoluble and begins to separate. Forming droplets, these dense helium raindrops sink through the metallic hydrogen layer towards Saturn's core, and as they settle, they release gravitational energy as heat. It's this ongoing process, still active today, that helps keep Saturn's temperature higher than expected. Cassini's measurements provided strong support for this helium rain model. The spacecraft's instruments detected less helium in Saturn's upper atmosphere than expected, indicating that this element is indeed being depleted as it migrates downward. The slow rain of helium toward the center continuously powers convection and helps delay Saturn's cooling, sustaining its peculiar warmth for billions of years. Saturn's lingering heat is also partially due to the energy left over from its formation. When Saturn first collapsed out of the primordial solar nebula, the vast amount of gravitational energy released during this process became trapped deep inside. While some of this energy has slowly leaked away, Saturn's size and gaseous composition make it an excellent insulator, meaning a significant amount of original heat is still making its way outward today. At extraordinary pressures, millions of Earth atmospheres, hydrogen transforms into a metallic liquid, conducting electricity and heat with great efficiency. This region near Saturn's core is a powerhouse for both magnetic field generation and internal energy transport. It acts as a furnace, warming the higher layers from below and helping drive the convection that ultimately produces turbulent clouds, powerful jet streams, and massive storms at the surface. Saturn's thermal structure is like a giant engine. Its deep interior is hot, but the upper layers are cold, especially at cloud tops. This steep temperature difference drives rise and fall of gas, churning up the planet's atmosphere, creating banded clouds, and fueling dynamic weather, especially the planet-encircling storms known as Great White Spots. Without this internal heat source, Saturn's atmosphere would settle into a quieter, far less eventful state. Uniquely, Saturn's heat budget requires both residual formation energy and helium rain, while Jupiter's internal heat can be mostly explained by leftover energy from formation alone. This subtle difference, caused by varying mass, internal structure, and evolution, demonstrates the diversity of giant planets both in our solar system and around other stars. Understanding Saturn's heat flow isn't just a curiosity, it has profound implications for interpreting ring systems, atmospheric phenomena, and the evolution of exoplanets. Saturn acts as a local laboratory for these exotic physics, giving planetary scientists a critical reference to unravel far more distant and mysterious worlds. The planet's rings themselves factor into this delicate balance. The shadows cast by the rings locally cool portions of the upper atmosphere, while the planet's warmth influences ring and moon chemistry through subtle exchanges of energy and magnetic effects. The entire Saturnian system, from rings to moons to the planet itself, is a web of energetic feedbacks, each influencing and being influenced by the planet's deep hot heart. Studying Saturn's hot internal clock reveals that even in the deep freeze of the outer solar system, remarkable processes hide beneath the clouds, processes that continue to shape the world and its complex environment today. Saturn's heat output is a clear marker of its ongoing internal activity. By measuring Saturn's effective temperature, about 95 Kelvin, which is roughly 20 degrees higher than what it would be if it only received and radiated heat from the sun, we see direct evidence of warmth rising from its interior. This difference isn't trivial. It's the fingerprint of deep processes like helium rain and the planet's slow, steady contraction that continue to generate energy even after billions of years. Over eons, Saturn will gradually lose this internal heat as helium rain slows and the last of its formation heat leaks out. But because Saturn is such an enormous, well-insulated planet, this cooling plays out on timescales stretching into billions of years, ensuring that for the foreseeable future, Saturn stays thermally vibrant beneath its clouds. The study of this process is far from complete. Exactly how helium settles out, what the core looks like, and the nature of turbulent convection are all still open questions. Cassini's flybys gave us gravity maps and atmospheric readings, but truly settling these mysteries will require future missions equipped with advanced probes or even instruments dropped deep into the atmosphere. Each improvement brings us closer to unraveling the secrets of gas giant evolution, interior structure, and energy flow. Saturn's heat isn't just a leftover from its birth. It's a dynamic, sustained phenomenon. The slow separation of helium, combined with long-term contraction, continues to power storms, influence Saturn's magnetic fields, and shape everything from jet streams to cloud bands. Deep inside, that hot clock is still ticking, radiating a quiet but powerful influence that determines much of what we see on and around this giant planet. Now consider Saturn's composition and what that means for its physical properties. Saturn is famously the least dense planet in the solar system, averaging only about 0.687 grams per cubic centimeter, significantly below the density of water. In other words, if you could find a cosmic swimming pool big enough, Saturn would float. While obviously hypothetical, this image captures a real truth about Saturn's makeup. It's a giant but not a heavy one, built largely from the lightest elements in the universe. Hydrogen, followed by helium, are the planet's main building blocks. These gases, even when compressed, remain much lighter than rock or metal. While there's likely a core with denser materials at Saturn's center, it makes up only a small fraction of the total volume. The rest is vast envelope upon envelope of hydrogen, sometimes molecular, deeper down metallic, surrounding the core and fluffing Saturn out to nearly 120,000 kilometers across at the equator. Moving inwards, Saturn's density does increase as gases are compressed by fierce gravity. The deepest layers may be dense metallic hydrogen, but when averaged over the entire colossal volume, core, fluids, and atmosphere together, the density remains low. This explains why the thought experiment of floating Saturn is more than a quirk. It's a powerful way to communicate the planet's true nature to anyone picturing the solid ground of home. Saturn's low density is also the reason for its iconic flattened shape, completing a full spin in just about 10.7 hours. Saturn rotates extremely quickly for its size. This rapid rotation spreads the planet's matter outward at the equator, making Saturn the most oblate, flattened at the poles and bulging at the equator of any planet in the solar system. Its equatorial diameter outstretches its polar diameter by nearly 11,800 kilometers, a difference you can even spot with high-powered telescopes. The effect is a direct result of how easily Saturn's hydrogen-rich body can be distorted by rotation. If Saturn were as rigid as Earth, it would resist this bulging, but its fluffy gases respond fluidly to the fast spin. The effect of Saturn's shape ripples outward. The planet's gravity field isn't uniform. The equator and poles experience slightly different pulls, which in turn affects the orbits of moons and the dynamics of Saturn's legendary rings. Precise gravity measurements from Cassini were essential for fine-tuning our models of Saturn's interior, especially the distribution and layering of mass below the cloud tops, and for understanding the slight wobbles in moon orbits and the structure of the rings. Saturn's low density and pronounced oblateness are not just surface features, they are clues about the invisible processes shaping the planet beneath the clouds. They tell us about the balance of forces, gravity, pressure, rotation, and the distribution of elements, and about Saturn's history as a rapidly formed gas giant that swept up billions of tons of hydrogen and helium from the primordial solar nebula. In turn, this makes Saturn an invaluable benchmark for understanding exoplanets, many of which show similarly low densities and huge radii, especially the hot Jupiters seen around other stars. Despite its lightweight bulk, Saturn's interior is anything but gentle. Pressures and temperatures soar toward the center, creating metallic hydrogen generating magnetic fields and sustaining heat-generating processes that power the planet's atmospheric dance. Its density tells a story that's both whimsical, floating in water, and deeply scientific, tying together formation, evolution, and ongoing activity. Saturn is a giant that's as physically elegant as it is revealing, an object whose simple statistics point to profound planetary truths. Saturn's pronounced oblateness isn't just a visible quirk, it's a central driver of the planet's overall system, affecting everything from atmospheric wind speeds to the way its rings and interior are structured. Because Saturn rotates so quickly and is made largely of hydrogen and helium, its equator bulges out significantly more than its poles. This creates not only a flattened appearance easily seen through even amateur telescopes, but also sets up important differences across the planet's atmosphere and interior. At the equator, that extra stretch changes how energy moves through the atmosphere. The thick, bulging equatorial region receives and traps solar energy differently than the flattened poles, and the geometry helps channel powerful zonal winds, those fast east-west bands that define Saturn's striped look. Cassini's instruments recorded astonishing wind speeds, especially near the equator, up to 1,800 kilometers per hour, reflecting the way the planet's oblate shape and rapid spin amplify atmospheric circulation. The uneven distribution of mass means the forces felt by clouds and gases vary smoothly from pole to equator, setting up the modulated bands and jet streams we observe. From an Earth-based perspective, Saturn's unique silhouette, wider at the equator, can be detected without special equipment, especially when the planet's ring tilt is just right. This makes Saturn's oblateness one of the most approachable examples of planetary physics visible to the public, anchoring its identity as a classic gas giant. But the effects run deeper. The oblate shape means Saturn's core must maintain perfect balance, centered despite immense outward force at the equator. This sets up complex 3D patterns of internal pressure, affecting everything from convection cells in the atmosphere to how heat and energy flow through the interior. Any model of Saturn's insides must factor in these non-spherical conditions, as pressure and gravity interact in subtle three-dimensional ways. Saturn's rings are an equally striking expression of this geometry. They lie perfectly within the equatorial plane, locked in by the planet's gravitational field, which itself is shaped by the equatorial bulge. The alignment isn't coincidence. Saturn's distinctive shape ensures the rings stay thin, tightly bound, and perfectly stable around the midsection, minimizing up and down wobbles that might otherwise disrupt them. Even Saturn's magnetic field appears linked to this symmetry. Unlike Earth or Jupiter, Saturn's magnetic field is closely aligned with its axis of rotation, a degree of perfection that's rare among planets. This precise match may be tied to the planet's nearly even, symmetric structure, the balance of spin, shape, and internal material producing a uniquely stable magnetic environment. While Saturn's rotation is fast, it's incredibly steady. The planet's massive moment of inertia makes any changes in spin rate extremely slow, preserving the degree of oblateness, the consistent orientation of the rings, and the stability of the moon system over millions of years. Astronomers see Saturn not only as a visual standout for its flattening, but as a living example of how rotation and fluidity sculpt planets on grand scales. Earth, by contrast, has only a tiny equatorial bulge about 21 kilometers, while Jupiter shows some flattening, but not to Saturn's extreme. Uranus and Neptune, rotating more slowly and possessing different compositions, are less distorted still. These lessons go beyond our solar system. When astronomers look for exoplanets and observe subtle bulges during planetary transits or spectral shifts, Saturn provides the gold standard for interpreting such clues. By understanding how rotation and mass distribution drive oblateness here, scientists can make better predictions about far-off giants circling other stars. In essence, Saturn's visible flattening isn't just for show, it's a direct window into the planet's physical makeup, the way gravity and rotation shape everything from cloud tops to the magnetic field and the layout of the rings. This elegant distortion is the signature of a dynamic, rapidly spinning, light-filled giant, a gateway to understanding the intricate workings of the solar system's most graceful planet.